Picture this. On a clear night away from city lights, you spot a faint, ghostly smudge among the stars. It doesn't look like much, just a barely visible patch most people would miss entirely. But here's what will blow your mind. You're seeing an entire galaxy containing 1 trillion suns, each potentially surrounded by worlds of their own. That light entering your eyes began its journey 2.5 million years ago, when our ancestors were just learning to walk upright. Even more incredible? This massive island universe, twice as large as our Milky Way, is hurtling toward us at over 250,000 miles per hour. In roughly 4.5 billion years, these two galactic giants will collide in the most spectacular cosmic event our region of space will ever witness. This is Andromeda, our nearest major galactic neighbor, and this is its story. Officially designated as Messier 31, or simply M31 in astronomical catalogues, Andromeda holds a special place in both astronomical history and our cosmic future. The galaxy's story in human consciousness stretches back over 1,000 years, to a time when the scientific method as we know it hadn't yet been conceived. The first recorded observation came from Persian astronomer Abd al-Rahman al-Sufi in 964 AD, who described it as a small cloud in his Book of Fixed Stars. This remarkable observer, working without telescopes or any optical aid beyond his own keen eyesight, catalogued this celestial object alongside his meticulous records of stars visible from the medieval Middle East. For centuries afterward, astronomers across different cultures noted this mysterious nebulous patch, speculating about its nature but lacking the tools to truly understand what they were observing. When we speak of Andromeda's immense scale, we're venturing into realms where human intuition begins to fail us, where numbers become so large they lose practical meaning. The galaxy spans roughly 220,000 light-years in diameter, a measurement so vast that light itself, traveling at 300,000 kilometers per second, would need 220,000 years to cross from one side to the other. This makes Andromeda significantly larger than our own Milky Way, which measures approximately 100,000 to 180,000 light-years across, depending on how you define its boundaries. Within this enormous cosmic structure exists approximately 1 trillion stars, about twice the stellar population of our home galaxy. Each of these stars is a sun in its own right, potentially hosting its own family of planets, moons, asteroids, and comets. The sheer magnitude of this stellar population staggers the imagination when you consider that our sun is just one of a few hundred billion stars in the Milky Way, and Andromeda contains twice that number. The galaxy displays a classic spiral structure, with graceful arms sweeping outward from a prominent central bulge. This bulge, a dense concentration of older reddish stars, dominates the galaxy's core region and gives Andromeda much of its distinctive appearance when photographed through powerful telescopes. The spiral arms themselves contain younger, bluer stars, mixed with vast clouds of gas and dust, the raw materials from which new stars continue to form. Unlike the Milky Way, which astronomers classify as a barred spiral galaxy due to the elongated bar structure extending through its center, Andromeda is an unbarred spiral, though recent observations have revealed complexities in its structure that challenge simple classifications. The galaxy's overall mass, when you include the dark matter halo surrounding it, reaches into the hundreds of billions or even trillions of solar masses, making it one of the most massive galaxies in our local cosmic neighborhood. The journey to understanding what Andromeda truly represents stands as one of astronomy's greatest detective stories, a tale of observational ingenuity, theoretical brilliance and paradigm-shifting discoveries that fundamentally altered humanity's place in the cosmos. Throughout the 17th, 18th, and 19th centuries, as telescopes improved and more astronomers turned their attention to the heavens, the number of known nebulae grew dramatically. These fuzzy patches of light puzzled observers who couldn't determine whether they were clouds of glowing gas within our own stellar system, or something else entirely. The great astronomer William Herschel, who discovered Uranus and revolutionized telescope design, believed nebulae were distant congregations of stars, but he lacked definitive proof. The debate intensified in the early 20th century, culminating in the famous Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis. Shapley argued that nebulae were relatively small objects within our galaxy, while Curtis contended they were island universes, separate galaxies comparable to our Milky Way, but located at enormous distances. Both astronomers presented compelling evidence for their positions, and the astronomical community remained divided. The resolution came 3 years later through the work of Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the world's largest and most powerful telescope. Hubble identified individual variable stars called Cepheids in Andromeda's spiral arms. These remarkable stars pulse with a regular rhythm, and crucially, their pulsation period directly correlates with their intrinsic brightness. By measuring how bright these stars appeared compared to how bright they actually were, Hubble could calculate their distance using simple geometry. The answer was shocking. Andromeda lay at least 900,000 light-years away, far beyond even the most generous estimates of the Milky Way's size. Modern measurements have revised this distance upward to approximately 2.5 million light-years, but Hubble's fundamental conclusion remained sound. Andromeda was indeed a separate galaxy, an entire stellar system comparable to our own, but separated by an almost incomprehensible gulf of empty space. This discovery expanded the known universe by orders of magnitude overnight. Suddenly, the Milky Way wasn't the entirety of creation, but merely one galaxy among countless others scattered throughout space. Humanity's cosmic address had changed forever. We weren't just inhabitants of Earth or citizens of the solar system, or even residents of the Milky Way alone. We belonged to a universe of galaxies, an expanding cosmos of staggering scale and complexity. Yet even as Hubble was measuring Andromeda's distance, other astronomers were discovering something equally remarkable about this neighboring galaxy. It's moving toward us. Using spectroscopy, which analyzes the light emitted or absorbed by celestial objects to determine their composition and motion, astronomers found that Andromeda's light is blue-shifted rather than red-shifted. In a universe where virtually every distant galaxy is rushing away from us due to cosmic expansion, causing their light to shift toward the red end of the spectrum, Andromeda's light shifts toward the blue, indicating approach rather than recession. These measurements reveal that the Andromeda Galaxy is hurtling toward the Milky Way at approximately 110 kilometers per second, or about 250,000 miles per hour. This might not sound particularly fast in cosmic terms, where galaxy recession velocities can reach significant fractions of light speed, but it's more than sufficient to seal the fate of both galaxies. Gravity, that most familiar yet mysterious of nature's fundamental forces, draws these two massive galaxies together in a slow-motion cosmic dance that will eventually end in merger. Despite the enormous distance currently separating them, gravitational interactions between Andromeda and the Milky Way have already begun. Computer simulations based on precise measurements of each galaxy's mass, position, and velocity show that the gravitational attraction between these two enormous structures has been accelerating them toward each other for billions of years. The collision won't happen tomorrow, or next century, or even in the next million years. Current models predict that the galaxies will begin their first close approach in approximately 4 to 4.5 billion years from now. This means Earth's Sun will spend more than half its remaining main sequence lifetime before the galactic merger begins, giving any future intelligent observers, if they exist, plenty of time to prepare for, or at least observe the cosmic spectacle. When we describe what's coming as a collision, it's important to understand what this actually means on galactic scales. The word conjures images of catastrophic impacts, of stars smashing together in violent explosions, of planetary systems being obliterated in fiery cataclysms. The reality, while still dramatic, is quite different and in many ways more fascinating. Galaxies, despite containing hundreds of billions or trillions of stars, are mostly empty space. The distances between individual stars are truly enormous compared to the star's actual sizes. Our Sun, for instance, is separated from its nearest stellar neighbour, Proxima Centauri, by about 4 light-years. To visualize this scale, imagine the Sun shrunk down to the size of a ping-pong ball. On this scale, Proxima Centauri would be another ping-pong ball, located roughly 680 kilometers away. The vast majority of the space between them contains absolutely nothing. Not even a single atom per cubic meter in most regions. This means that when Andromeda and the Milky Way collide, direct collisions between individual stars will be extraordinarily rare, possibly non-existent. Stars will pass by each other like ships in an enormous dark ocean, likely never coming close enough to gravitationally disturb each other's planetary systems significantly. However, while star-on-star collisions won't occur, the galaxies themselves will experience profound gravitational disruption. As these two massive structures interpenetrate, their gravitational fields will interact in complex ways, pulling streams of stars and gas out into long tidal tails, triggering intense bursts of star formation where gas clouds collide and compress, and generally wreaking havoc on the organized spiral structures both galaxies currently display. The merger won't be a simple, one-time event. Current simulations show that Andromeda and the Milky Way will pass through each other completely during their first encounter, with the galaxies' gravitational interaction sending them tumbling past one another like two dancers spinning after an embrace. But gravity is patient and inexorable. The two galaxies will slow down, halt their mutual recession, and fall back together for a second pass-through. This process will repeat, with each subsequent encounter bringing the galaxies' cores closer together, the merger becoming progressively more violent and chaotic as momentum and angular momentum are exchanged and radiated away through various complex gravitational mechanisms. Over a period of perhaps 2 billion years, through multiple approaches and pass-throughs, the two galaxies will gradually settle down, their separate identities erased, their stars mixed together into a new configuration. The final product of this grand merger will likely be a giant elliptical galaxy, lacking the spiral structure of its progenitors, but containing all their stars jumbled together in a more or less spherical or football-shaped distribution. Astronomers, displaying the dry humor often found in scientific circles, have already nicknamed this future galaxy Milkomeda, or sometimes Milkdromeda, a portmanteau of its parent galaxy's names. Milkomeda will be one of the larger galaxies in the local group, the small cluster of galaxies to which both the Milky Way and Andromeda currently belong. What will this mean for Earth and our solar system? The answer is both reassuring and sobering. As mentioned, direct stellar collisions are unlikely, so the Sun probably won't be destroyed in a stellar traffic accident. However, the gravitational perturbations during the merger could eject our solar system from the galactic disk entirely, sending us wandering through the galactic halo or even into intergalactic space. Alternatively, we might find ourselves flung toward the center of the newly forming Milkomeda, placed in a very different stellar neighborhood than we currently occupy. From Earth's surface, if anyone or anything is still here to watch, the night sky will transform dramatically, with Andromeda growing larger and larger over millions of years until it fills a significant portion of the celestial sphere, its spiral structure becoming ever more distorted and chaotic as the merger progresses. Of course, these concerns about Earth's fate during the merger may be entirely academic. Astrophysicists predict that in about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its evolution off the main sequence, swelling into a red giant star that will likely engulf Mercury, Venus, and possibly Earth itself. This solar evolution will occur around the same time as the galactic collision begins, meaning Earth's fate may be sealed by our star's death throes before the galactic merger poses any threat. Still, the merger itself represents one of the most significant events in our local cosmic future, an apocalyptic transformation that will fundamentally reshape the stellar environment for hundreds of billions of stars and any planets and possibly civilizations that orbit them. Andromeda doesn't travel alone through space. Like our Milky Way, which is accompanied by the Magellanic Clouds and several dozen smaller dwarf galaxies, Andromeda presides over its own system of satellite galaxies, smaller stellar systems bound to it by gravity and orbiting around it like planets around a star. The two brightest of these companions are easily visible through modest telescopes and were catalogued by Charles Messier in the 18th century as M32 and M110, though they were certainly observed by earlier astronomers. M32 is a compact elliptical galaxy, one of the smallest known examples of this galaxy type, appearing almost star-like in small telescopes due to its high concentration. M110 is also an elliptical galaxy, but larger and more diffuse than M32, with a more extended distribution of stars. Beyond these two prominent companions, astronomers have identified at least 14 satellite galaxies orbiting Andromeda, and recent surveys suggest there may be many more awaiting discovery. These satellites range from relatively substantial dwarf galaxies containing millions or billions of stars down to ultra-faint systems with only a few tens of thousands of stars, barely distinguishable from globular clusters. Finding these faint satellites requires painstaking searches through astronomical survey data, looking for subtle overdensities of stars with similar distances and motions that betray their gravitational association with Andromeda. Each newly discovered satellite adds to our understanding of galactic hierarchy and structure, revealing how large galaxies like Andromeda and the Milky Way sit at the centers of extended families of smaller systems. These satellite galaxies aren't merely passive bystanders in Andromeda's evolution. Evidence suggests that at least some of them will eventually be consumed by their massive host, adding their stars to Andromeda's total population in miniature versions of the Grand Merger, awaiting Andromeda and the Milky Way. This process of galactic cannibalism is thought to be one of the primary ways that large galaxies like Andromeda grow over cosmic time, gradually accumulating mass by consuming smaller neighbors. The discovery and study of Andromeda's satellites therefore provides crucial insights into how galaxy clusters form and evolve, how dark matter is distributed on various scales, and how the hierarchical structure of the universe develops from small-scale structures merging to form progressively larger ones. Speaking of dark matter, this mysterious substance plays a crucial role in Andromeda's structure and dynamics, despite being completely invisible to all our telescopes, regardless of what wavelength they observe in. Like all large galaxies, Andromeda is embedded in an enormous halo of dark matter, an extended cloud of this unknown material that surrounds the visible galaxy and extends far beyond its luminous boundaries. Scientists estimate that this dark matter halo stretches for at least 1 million light-years from Andromeda's center, possibly much farther, and contains several times more mass than all the visible stars, gas, and dust in the galaxy combined. The dark matter halo may actually extend all the way to the Milky Way and beyond, meaning we might already be passing through the outermost regions of Andromeda's dark matter distribution, even though the visible parts of the galaxy remain millions of light-years away. We know this dark matter exists not through direct observation, but through its gravitational effects on visible matter. Astronomers can measure how fast stars and gas clouds are moving at various distances from Andromeda's center. According to Newton's laws of gravity and motion, objects orbiting farther from a galaxy's center should move more slowly, just as outer planets in our solar system orbit more slowly than inner planets. However, observations show that rotation speeds in galaxy disks remain roughly constant, or even increase slightly at large distances from the center, a phenomenon called flat rotation curves. The only explanation that fits the observations is that galaxies contain vast amounts of additional mass that we cannot see directly. This invisible mass, dubbed dark matter, provides the extra gravitational pull needed to keep outer stars moving at their observed speeds. The nature of dark matter remains one of physics' greatest unsolved mysteries. We know it doesn't emit, absorb, or reflect electromagnetic radiation, making it invisible to all conventional observational methods. It doesn't seem to interact with normal matter except through gravity. Various candidates have been proposed, from exotic subatomic particles with names like WIMPs, weakly interacting massive particles, and axions to more radical ideas involving modifications to our understanding of gravity itself. Despite decades of searching, particle physics experiments have yet to detect dark matter particles directly, though the gravitational evidence for its existence is overwhelming. Andromeda's dark matter halo, along with those of countless other galaxies, stands as testament to how much of our universe remains mysterious, how much we have yet to learn about the fundamental nature of matter and energy. Turning our attention to Andromeda's central regions, we find a dense stellar metropolis surrounding a supermassive black hole at the galaxy's exact center. This black hole, like the one at the heart of our Milky Way, represents a fundamental component of large galaxy structure. Measurements based on the motions of stars and gas near Andromeda's center indicate the black hole has a mass of approximately 100 to 200 million times that of our Sun. To put this in perspective, the supermassive black hole at our Milky Way's center, called Sagittarius A, weighs in at about 4 million solar masses, making Andromeda's central black hole roughly 25 to 50 times more massive than our own. This enormous mass is concentrated in a region smaller than our solar system, creating gravitational forces so intense that not even light can escape from within the black hole's event horizon. Around this monster black hole, stars crowd together in incredible densities. Near the very center, individual stars pass within astronomical units of each other, distances comparable to planetary separations in our solar system. Compare this to our Sun's neighborhood, where the nearest star is 4 light-years away. In Andromeda's core, you could potentially see neighboring stars as bright, distinct disks rather than mere points of light, assuming you could somehow survive in such an environment. These central stars orbit at tremendous velocities, whipping around the black hole at speeds that reach into the thousands of kilometers per second. Studying these motions allows astronomers to precisely measure the black hole's mass and study how gravity behaves in these extreme conditions, where Einstein's general relativity significantly modifies the classical Newtonian predictions. The supermassive black hole itself is thought to grow through 2 primary mechanisms. First, it can accrete gas and dust from its surroundings, with material spiraling inward through an accretion disk, heating to tremendous temperatures through friction, and eventually crossing the event horizon and adding to the black hole's mass. Second, black holes can grow by merging with other black holes. When Andromeda eventually collides with the Milky Way, their 2 supermassive black holes will likely spiral together and merge, creating an even more massive black hole at the center of Milkomeda. This merger will be accompanied by tremendous releases of energy in the form of gravitational waves, ripples in space-time itself that will propagate outward at light speed, potentially detectable by future gravitational wave observatories if any advanced civilizations are watching. Despite the dramatic environment of Andromeda's core, star formation continues in other regions of the galaxy, particularly in the spiral arms where gas and dust remain abundant. These star-forming regions appear as bright knots and patches in images of Andromeda, particularly visible when the galaxy is photographed in ultraviolet or hydrogen alpha wavelengths that highlight hot young stars and ionized gas. The process of star formation follows the same basic pattern throughout the universe. Vast clouds of molecular hydrogen, sometimes mixed with dust and trace amounts of heavier elements, slowly contract under their own gravity. As these clouds collapse, they fragment into smaller clumps, each of which may eventually form a star or multiple stars in a stellar system. The exact details depend on many factors, including the cloud's temperature, density, rotation rate, and magnetic field strength. In Andromeda's spiral arms, density waves propagating through the galactic disk compress gas clouds as they pass through, triggering star formation along the arm's leading edges. This is why spiral arms appear bright and blue in images. They're outlined by recently formed massive blue stars, which are extremely bright but short-lived, lasting only millions of years before exploding as supernovae. By contrast, the longer-lived but dimmer red stars that make up most of the stellar population are more evenly distributed throughout the galaxy. The rate of star formation in Andromeda has varied over the galaxy's history. Currently, Andromeda produces approximately 1 solar mass worth of new stars per year, which sounds impressive until you realize the galaxy contains 1 trillion solar masses in stars already. This means Andromeda is forming new stars at a relatively sedate pace compared to some galaxies, particularly compared to starburst galaxies, where collisions or interactions have triggered intense episodes of star formation that consume available gas in mere hundreds of millions of years. The star-forming regions in Andromeda's spiral arms appear as bright blue patches because massive young stars emit most of their light at shorter, bluer wavelengths. These same regions also shine brightly in infrared observations, where the warm dust heated by young stars re-radiates energy at longer wavelengths. Astronomers can identify star-forming regions by looking for emissions from ionized hydrogen gas, which produces a characteristic red glow called hydrogen alpha emission. The intense ultraviolet radiation from hot young stars strips electrons from hydrogen atoms in surrounding gas clouds, creating regions of ionized hydrogen called H2 regions that shine with this distinctive red color. By mapping these HII regions, astronomers can trace where star formation is occurring throughout the galaxy and understand how the rate and location of star formation have changed over time. Among the most perplexing features of Andromeda is the peculiar double nucleus at its center, a mystery that puzzled astronomers for years after its discovery. When examining high-resolution images of Andromeda's core, particularly those taken by the Hubble Space Telescope, astronomers noticed something strange. Instead of a single, symmetrical concentration of light at the galaxy's center, there appeared to be two bright clusters of stars, separated by about 5 light-years. This double nucleus raised fundamental questions. Did Andromeda somehow have two centers? Could it contain two supermassive black holes that hadn't yet merged? Was one of these concentrations the remnant core of a smaller galaxy that Andromeda had recently consumed? After careful analysis of stellar motions and light distributions, astronomers developed the currently favored explanation. One of the two bright concentrations is indeed the true center of the galaxy, marking the location of the supermassive black hole. The other is actually a disk of old red stars orbiting the central black hole at a distance of a few light-years. We're seeing this disk almost edge on from our vantage point in the Milky Way, which makes it appear as a distinct bright spot rather than spread out across the sky. The disk itself likely formed from stars that were captured into orbit around the black hole when a smaller galaxy merged with Andromeda in the distant past. These stars, initially part of the infalling satellite galaxy, were gradually redistributed through gravitational interactions into an eccentric disk orbiting the central black hole. This double nucleus structure tells us something important about Andromeda's violent history. Galaxies, we now understand, don't evolve in isolation. They collide, merge, consume their smaller neighbors, and are occasionally consumed themselves by even larger neighbors. Each of these interactions leaves traces in the galaxy's structure, like archaeological layers recording ancient events. The double nucleus is one such trace, evidence of at least one significant merger in Andromeda's past. But it's far from the only evidence. When astronomers map the distribution of stars in Andromeda's outer halo, they find streams and clumps, coherent structures that stand out from the smooth background distribution. These stellar streams are the torn-apart remnants of dwarf galaxies that Andromeda has consumed over billions of years. The story these stellar streams tell is one of ongoing galactic cannibalism. As a small satellite galaxy orbits around Andromeda, the tidal forces exerted by Andromeda's gravity pull stars from the near and far sides of the satellite, stretching it along its orbital path. Over time, the satellite is completely disrupted, its stars spread out into a long stream that wraps around Andromeda. These streams can persist for billions of years, slowly mixing into the general halo population, but remaining detectable as overdensities of stars with similar positions and velocities. By identifying and studying these streams, astronomers can reconstruct Andromeda's merger history, determining approximately when various satellite galaxies were consumed and what their properties were before they met their fate. Multiple stellar streams have been identified in Andromeda's halo, each representing a separate merger event. One particularly prominent stream, called the Giant Southern Stream, contains the remnants of a galaxy that was likely about 20 times more massive than the dwarf spheroidal satellites orbiting Andromeda today. The disruption of this galaxy probably occurred sometime between 1 and 3 billion years ago. Another structure, called the Northeast Shelf, represents a more recent merger, possibly still ongoing. These discoveries paint a picture of Andromeda as an aggressive cannibal galaxy that has grown to its current large size in part by consuming many smaller neighbors over cosmic time. The Milky Way has a similar history, and the future merger between Andromeda and the Milky Way represents the next chapter in this continuing story of galactic growth through hierarchical merging. Recent observations have revealed another mystery in Andromeda's structure related to its rotation. You might expect a galaxy to rotate fairly simply, like a spinning disk or a wheel, with all parts moving in the same direction at speeds that depend primarily on their distance from the center. While galaxies do rotate in this general sense, detailed observations reveal complications. In Andromeda's case, astronomers discovered that the galaxy's outer regions, particularly the extensive disk of stars and gas beyond the prominent spiral arms, show peculiar rotational characteristics. Some regions appear to be rotating in the opposite direction relative to the main galaxy, while other regions show evidence of warping, with the disk tilted at different angles at different distances from the center. These peculiarities likely result from Andromeda's merger history. When a satellite galaxy is consumed, its stars don't immediately settle into circular orbits aligned with the main galaxy's disk. Instead, they retain much of their original angular momentum, creating a population of stars on more elliptical or inclined orbits. If the satellite's orbital motion was retrograde relative to Andromeda's overall rotation, the accreted stars will also have retrograde motion, creating the observed counter-rotating populations. Similarly, if a satellite merged while approaching from above or below Andromeda's disk plane, the resulting stellar populations might show vertical motions that contribute to the observed warping. The presence of these features tells us that Andromeda's structure is not in equilibrium, but is still adjusting to past merger events, a process that can take billions of years for a galaxy this large. The rotation mystery extends to observations of a massive rotating disk of stars in Andromeda's outer regions, detected through careful measurements of stellar velocities. This disk appears to extend far beyond the visible spiral arms and contains a substantial fraction of the galaxy's total stellar mass. Its existence challenges and refines models of how large spiral galaxies form and evolve. In the simplest models of galaxy formation, stars should form primarily in the main disk, with relatively few stars in the outer halo regions. The discovery of this extended rotating disk suggests that galaxy formation is more complex, possibly involving multiple episodes of star formation in various environments, or significant redistribution of stars after they form through merger events and other dynamical processes. From Earth, Andromeda holds the distinction of being the most distant object reliably visible to the unaided human eye under good conditions. On a clear, dark night, far from city lights, you can see Andromeda as a faint, elongated smudge in the constellation that shares its name. This simple observation connects us directly to the deep cosmos in a way that few other naked-eye objects can. The Moon and planets are neighbors, located within our solar system. The stars we see are members of our own Milky Way galaxy, generally within a few thousand light-years of Earth. But Andromeda, that faint patch of light, represents an entire galaxy, a separate stellar city containing 1 trillion suns, situated millions of light-years away across intergalactic space. When you observe Andromeda, whether with the naked eye, binoculars, or a telescope, you're engaged in an act of cosmic time travel. The light entering your eyes began its journey across the universe 2.5 million years ago, when that light was emitted from Andromeda's stars. Earth was a very different place. Our genus Homo had not yet appeared. Australopithecines, early hominins with brains about 1/3 the size of modern humans, were roaming the African savanna. No human had yet learned to make fire, let alone build civilizations, develop writing, or construct telescopes. The light has been traveling through empty space all this time, crossing millions of light years of intergalactic void, until finally some of those ancient photons happen to strike your retina or telescope optics, bringing us information about Andromeda as it existed in the incredibly distant past. For amateur astronomers, Andromeda offers various observing opportunities depending on equipment. With the naked eye, you can see the galaxy's bright central core as a fuzzy patch, appearing roughly as large as the full moon on the sky despite its enormous distance. Binoculars reveal more detail, showing the galaxy's elongated shape and perhaps hints of the dust lanes that run through the disk. Small telescopes make the dust lanes clearly visible and may show the two brightest satellite galaxies, M32 and M110, as small fuzzy patches near the main galaxy. Medium to large amateur telescopes can reveal structure in the spiral arms and show some of the brighter globular clusters orbiting Andromeda. Long exposure photographs, even those taken with high-end consumer cameras, can capture stunning detail showing the full extent of Andromeda's spiral arms stretching across several degrees of sky. Professional observatories have studied Andromeda across the entire electromagnetic spectrum, revealing different aspects of the galaxy's structure and composition. In visible light, we see primarily the stars themselves, with the brightest young blue stars prominent in the spiral arms and older red stars dominating the central bulge. The dust lanes, vast clouds of tiny solid particles mixed with gas, appear as dark streaks silhouetted against the background starlight. Moving to infrared wavelengths, which penetrate dust more effectively than visible light, the distribution of cool dust becomes apparent, glowing with heat absorbed from stars and re-radiated at longer wavelengths. Infrared observations also reveal cooler red giant stars and highlight star-forming regions where warm dust surrounds nascent stellar nurseries. Ultraviolet observations show a completely different aspect of Andromeda, highlighting the hottest stars and most vigorous star-forming regions. Massive young stars emit most of their energy in the ultraviolet, causing them to shine brightly in UV images while being relatively inconspicuous in visible light. These observations help astronomers understand where star formation is currently most active and measure the rate at which new stars are being born. X-ray observations reveal yet another population of objects, including neutron stars and black holes in binary systems, where they're accreting material from companion stars, as well as the hot gas in Andromeda's halo, heated to millions of degrees by supernovae and stellar winds. Radio observations map the distribution of cold neutral hydrogen gas, the raw material for future star formation, showing how this gas is distributed throughout the galaxy and how much fuel remains for making new stars. Each wavelength regime provides unique information, and combining observations across the spectrum gives us a comprehensive understanding of Andromeda's structure, composition, and evolution. Modern multi-wavelength surveys have mapped Andromeda in unprecedented detail, resolving individual stars across much of the galaxy and allowing astronomers to study stellar populations, star formation, and galactic structure with remarkable precision. The Hubble Space Telescope's panchromatic Hubble Andromeda Treasury Survey, for instance, imaged large sections of Andromeda's disk with resolution sufficient to separate individual stars, creating a dataset containing over 100 million stellar measurements that astronomers continue to analyze today. One of the most intriguing questions about Andromeda concerns planets. We know that planets are common in our galaxy, orbiting the majority of stars and possibly outnumbering stars when you count all planet types. There's no reason to think Andromeda would be any different. With 1 trillion stars, Even conservative estimates suggest tens or hundreds of trillions of planets orbiting stars throughout that galaxy. Some fraction of these planets will be rocky worlds located in their stars' habitable zones, where temperatures allow liquid water to exist on planetary surfaces. Given Earth's example, some of these worlds might develop life, and some of that life might eventually develop intelligence and technology. The famous Drake equation, which estimates the number of communicating civilizations in a galaxy based on factors like star formation rate, planet frequency, and the probability of life developing, suggests that large galaxies like Andromeda could harbor multiple technological civilizations at any given time, though the uncertainties in each factor make this highly speculative. However, despite the likely abundance of planets in Andromeda, detecting them individually presents extraordinary challenges. The methods we use to find planets around nearby stars all rely on measuring tiny effects that become nearly impossible to detect at Andromeda's distance. The transit method, which detects planets by the tiny dimming they cause when passing in front of their stars, requires monitoring individual stars' brightness with extreme precision. While we can resolve individual bright stars in Andromeda, they're so far away that achieving the photometric precision needed for transit detection is currently impossible for all but the very brightest stars. The radial velocity method, which detects planets by the tiny wobbles they induce in their stars' motions, requires high-resolution spectroscopy of individual stars, again extremely difficult at such distances. Direct imaging of exoplanets, already challenging in our own galaxy, becomes essentially impossible at intergalactic distances. Even the most powerful telescopes cannot resolve the tiny angular separation between an Andromeda star and any planets orbiting it, and the planet's faint reflected light would be utterly overwhelmed by the star's glare. There have been a few claims of possible planet detections in Andromeda using gravitational microlensing, where a planet passing in front of a more distant star temporarily brightens it through gravitational lensing effects. But these remain controversial and unconfirmed. For now, our knowledge of planets in Andromeda remains statistical rather than observational. We can confidently predict that trillions of planets exist there based on what we've learned about planet formation in our own galaxy. But we cannot yet point to a specific planet and say, there is a world orbiting that star in Andromeda. This situation may change as technology advances. Future extremely large telescopes with mirrors 30 meters or more in diameter may be able to detect the brightest transiting exoplanets around Andromeda's most luminous stars. Even more promising, space-based observatories designed specifically for exoplanet detection and characterization might achieve the stability and sensitivity needed to find planets in nearby galaxies. Within a few decades, we may finally be able to confirm the existence of specific worlds in Andromeda, planets orbiting alien suns in a separate galaxy, potentially even detecting biosignatures in their atmospheres that might hint at the presence of life. Until then, we can only imagine what worlds exist there, what landscapes and sunrises might grace those distant planets, whether anyone or anything might be looking back across the intergalactic gulf toward the Milky Way with similar curiosity. From a scientific perspective, Andromeda serves as an invaluable laboratory for understanding galaxies in general and our own Milky Way in particular. When studying the Milky Way, astronomers face a fundamental challenge. We're inside it. Imagine trying to understand the architecture of a city while standing at street level in the middle of it. You can see buildings nearby in detail, but your view of the overall layout, the city's shape and structure, is limited by your perspective. Now imagine viewing that same city from an airplane or satellite. Suddenly, the overall pattern becomes clear. You can see how neighborhoods connect, identify the main thoroughfares, understand the relationship between different districts. This is precisely the advantage Andromeda gives us for understanding spiral galaxies. We have an external, face-on view that reveals large-scale structures and patterns difficult or impossible to observe from our position embedded within the Milky Way's disk. By studying Andromeda, astronomers can observe how spiral density waves propagate through galactic disks, how star formation is distributed spatially throughout a large spiral galaxy, how the stellar populations vary from the core to the outer regions, and how the overall architecture of spiral arms relates to the galaxy's rotation and mass distribution. These insights can then be applied back to understanding the Milky Way. When we measure something about Andromeda's structure, we can reasonably assume the Milky Way, being a similar type of galaxy, probably has comparable features. This comparative approach has been essential in developing our modern understanding of galactic structure and evolution. Andromeda also serves as a template for understanding how spiral galaxies evolve over cosmic time. By studying the stellar populations at different locations within the galaxy, astronomers can reconstruct its history. The central bulge contains primarily old red stars that formed billions of years ago when the galaxy was young. The oldest stars in this region date back roughly 10 billion years, nearly to the beginning of the universe itself. These ancient stars formed from gas that contained relatively few heavy elements, since multiple generations of stars had not yet lived and died to enrich the interstellar medium with the products of nuclear fusion. As a result, these old stars have low metallicities, using astronomers' terminology where any element heavier than helium is called a metal, regardless of its chemical properties. Moving outward from the bulge into the disk, we find progressively younger stellar populations on average, with the spiral arms containing the youngest stars still forming today. This radial gradient in stellar ages suggests that Andromeda, like most large galaxies, formed from the inside out. The central regions collapsed and formed stars first, while the outer regions took longer to accumulate enough material to begin significant star formation. However, the picture is more complex than simple inside-out formation. The stellar streams and the peculiar rotation patterns we discussed earlier indicate that mergers have significantly complicated Andromeda's formation history. Some stars in the outer regions are quite old, possibly having formed in satellite galaxies before those satellites were consumed, and their stars redistributed throughout Andromeda's halo. The approximately 450 globular clusters orbiting Andromeda provide another window into the galaxy's formation and evolution. Globular clusters are remarkable objects, spherical collections of hundreds of thousands to millions of stars packed into regions just tens of light years across. These clusters orbit in the halo surrounding the galaxy, following elliptical paths that take them far above and below the galactic disk. What makes globular clusters particularly interesting is their extreme age. Most formed very early in the universe's history, within a billion years or so of the Big Bang. The stars in these clusters are therefore among the oldest objects we can study, fossil remnants from the epoch when galaxies were just beginning to assemble. Andromeda's globular cluster system is significantly richer than the Milky Way's, with roughly 3 times as many clusters. This difference tells us something about the galaxy's formation histories. The number of globular clusters a galaxy possesses correlates with how many mergers it has experienced, since mergers can trigger bursts of globular cluster formation and also add the victim galaxy's clusters to the surviving galaxy's collection. Andromeda's abundant globular cluster system therefore provides additional evidence for its active merger history. By studying the ages, compositions, and orbital properties of these clusters, astronomers can constrain when various merger events occurred and what the properties of the merged galaxies were. Globular clusters also serve as laboratories for studying stellar evolution under extreme conditions. The high stellar densities in cluster cores lead to frequent close encounters between stars, occasionally resulting in exotic objects like blue stragglers, which are stars that appear younger and more massive than they should, be given the cluster's age, likely formed through stellar collisions or mergers. Globular clusters also host populations of X-ray binary systems, where a neutron star or black hole accretes material from a companion star, and millisecond pulsars, rapidly spinning neutron stars that were spun up through accretion. Studying these exotic objects in Andromeda's globular clusters helps astronomers understand stellar evolution in dense environments and tests theories of stellar dynamics and binary star evolution. Beyond the visible galaxy, beyond even the stellar halo and globular clusters, Andromeda is surrounded by an extended gaseous halo that stretches for hundreds of thousands of light years in all directions. This halo, composed primarily of hot ionized hydrogen and helium, heated to temperatures of hundreds of thousands or even millions of degrees, contains about half the mass of all the visible stars in the galaxy. The gas is so diffuse and hot that it emits, primarily in the ultraviolet and X-ray portions of the spectrum, making it invisible to optical telescopes but detectable with space-based UV and X-ray observatories. The existence of this enormous reservoir of hot gas raises fundamental questions about galaxy evolution. Where did this gas come from? Why hasn't it cooled and fallen into the galaxy to form new stars? The leading explanation involves a process called galactic feedback. Stars, particularly massive ones, don't just shine passively during their lives. They blast out powerful stellar winds that drive gas away from star-forming regions. When massive stars explode as supernovae, they inject tremendous amounts of energy into the surrounding gas, heating it to millions of degrees and driving it outward at high velocities. If conditions are right, this gas can be driven completely out of the galactic disk into the halo, creating what's called a galactic fountain. If the gas reaches high enough velocities, a galactic wind that removes gas from the galaxy entirely. Meanwhile, gas also falls into galaxies from the intergalactic medium, providing fresh fuel for star formation. The balance between inflows and outflows, mediated by star formation and the feedback it generates, determines how galaxies evolve over cosmic time. Andromeda's extended gaseous halo represents material that has been enriched with heavy elements by stellar processes, ejected from the disk by supernovae and stellar winds, but hasn't yet escaped the galaxy's gravitational pull. Some of this gas will eventually cool and rain back down onto the disk, recycling back into star formation after spending billions of years in the halo. Other portions may remain in the halo indefinitely, or escape the galaxy entirely if they gain sufficient velocity. Understanding this cycle of gas inflow, star formation, feedback, and outflow is crucial for understanding why galaxies have the properties they do, including why they contain far fewer stars than simple models predict they should. Based on the amount of gas available for star formation over cosmic time, recent observations using ultraviolet spectroscopy have mapped Andromeda's gaseous halo by observing how it absorbs light from more distant background objects, typically quasars whose light passes through the halo on its way to Earth. These observations reveal that the halo contains multiple phases of gas at different temperatures, from relatively cool clouds at tens of thousands of degrees to diffuse, hot gas at millions of degrees. The halo is not uniform but shows structure, with some regions denser than others. This structure likely reflects Andromeda's merger history, with some of the dense regions representing gas stripped from infalling satellite galaxies. The halo also shows evidence of rotation, though slower than the galaxy's disk, and exhibits complex kinematics that scientists are still working to fully understand. When we observe Andromeda across different wavelengths of light, each view reveals different components and processes within the galaxy. Visible light observations show the integrated light from billions of stars, allowing us to trace the galaxy's spiral structure and study stellar populations. In these images, the dust lanes appear as dark streaks, where interstellar dust absorbs starlight, particularly in the blue part of the spectrum. The central bulge glows with a yellowish color characteristic of old red giant stars, while the spiral arms show a bluer tint from young, hot stars. Long exposure photographs by skilled astrophotographers reveal incredibly detailed views of Andromeda's structure, sometimes showing faint structures in the outer halo that are barely visible, even in professional survey data. Infrared observations penetrate the dust that obscures parts of Andromeda in visible light, revealing the structure of the dust itself and the stars hidden behind it. Near-infrared wavelengths, roughly 1 to 3 microns, show primarily light from stars, particularly cool red giants that emit most of their energy at these wavelengths. Mid-infrared observations from about 3 to 30 microns reveal warm dust heated by stars to temperatures of a few hundred degrees Kelvin. This dust emits thermal radiation in the mid-infrared, tracing star formation regions where dust is heated by newly formed stars. Far infrared observations at wavelengths longer than 30 microns detect cooler dust at temperatures of just a few tens of degrees Kelvin, revealing the coldest dust reservoirs in the galaxy. Ultraviolet observations highlight the hottest, most massive stars, which emit the bulk of their energy at these short wavelengths. UV images of Andromeda show the spiral arms illuminated by young, hot stars with surface temperatures of tens of thousands of degrees. These are precisely the stars that live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae. Because they're so short-lived, their presence indicates recent star formation. By mapping where these hot stars are located, astronomers can determine where star formation is currently occurring and measure the star formation rate across different regions of the galaxy. X-ray observations reveal the highest energy phenomena in Andromeda. X-ray binary systems, where a compact object like a neutron star or black hole accretes material from a companion star, shine brightly in X-rays as the infalling material heats to temperatures of millions of degrees before crossing the event horizon or impacting the neutron star surface. Supernova remnants, the expanding shells of gas blasted into space by stellar explosions, emit X-rays as they plow into surrounding gas and heat it through shockwaves. The hot gas in Andromeda's halo also emits soft X-rays, providing information about the temperature and density of this diffuse material. The central supermassive black hole, while not currently very active, occasionally flares in X-rays when it accretes small amounts of gas, or when stars pass close enough to be tidally disrupted. Radio observations map the distribution of cold neutral hydrogen gas throughout Andromeda. This gas, at temperatures of just tens to hundreds of degrees Kelvin, exists in vast clouds throughout the galaxy's disk and provides the raw material for future star formation. Radio telescopes can detect the characteristic 21 centimeter emission line of neutral hydrogen, allowing astronomers to map not just where this gas is located, but also how it's moving. By measuring Doppler shifts in the 21 centimeter line, radio astronomers can determine the rotation curve of Andromeda, measuring how fast gas at various distances from the center is orbiting the galaxy. These rotation curve measurements provided some of the early evidence for dark matter in galaxies and continue to constrain models of how dark matter is distributed. Radio observations also detect emission from supernova remnants and from the electrons spiraling through magnetic fields in a process called synchrotron radiation. This reveals the distribution and strength of magnetic fields in Andromeda's disk and halo. Additionally, radio observations can detect complex organic molecules in star-forming clouds, providing insights into the chemistry occurring in these regions and the raw materials available for planet formation. The combination of all these multi-wavelength observations builds a comprehensive picture of Andromeda as a complex, dynamic system with ongoing physical processes operating across a vast range of scales, from the supermassive black hole at the center to the extended halo stretching hundreds of thousands of light-years into intergalactic space. The question of planetary systems in Andromeda deserves deeper consideration given what we've learned about planets in our own galaxy. Over the past 3 decades, since the first confirmed detection of a planet orbiting another Sun-like star in 1995, astronomers have discovered thousands of exoplanets in the Milky Way. These discoveries have revolutionized our understanding of planet formation and revealed that planetary systems are incredibly diverse. We've found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. We've discovered super-Earths, rocky planets more massive than Earth but smaller than Neptune, a planet type that doesn't exist in our solar system. We've found planets orbiting binary star systems, planets orbiting pulsars, rogue planets floating freely through space unbound to any star. Statistical analyses of planet detection surveys suggest that essentially every star hosts at least one planet on average, with many stars hosting multiple planets. A significant fraction of Sun-like stars, perhaps 20% or more, host rocky planets in their habitable zones where temperatures could allow liquid water on planetary surfaces. Extrapolating these statistics to Andromeda, with its trillion stars, suggests truly staggering numbers of planets. There could be 1 trillion or more planets in total, with tens or hundreds of billions of rocky worlds, and billions or tens of billions of potentially habitable planets. Some of these worlds might harbor life, perhaps even intelligent life, though the uncertainties in estimating the probability of life arising and developing intelligence mean we cannot make confident predictions about whether Andromeda actually hosts other civilizations. The challenge of detecting individual planets in Andromeda remains formidable with current technology. The angular resolution required to spatially separate a planet from its star at Andromeda's distance exceeds the capabilities of even our most powerful telescopes by several orders of magnitude. The brightness contrast between stars and planets, already challenging in our own galaxy where we can detect only a handful of planets through direct imaging, becomes utterly prohibitive at intergalactic distances. However, astronomers are creative, and several proposed future techniques might eventually allow planet detection in nearby galaxies like Andromeda. One possibility involves detecting transits of planets across stars during gravitational microlensing events. When one star passes almost directly in front of another, more distant star from our perspective, the foreground star's gravity acts as a lens, temporarily brightening the background star. If the foreground star hosts a planet, the planet can create a distinctive signature in the lensing light curve. While standard transit detection requires monitoring specific stars continuously, microlensing can potentially detect planets around any star that happens to lens a background source, including stars in other galaxies. However, such events are incredibly rare, and detecting them would require monitoring millions of stars continuously and being lucky enough to catch the right configuration at the right time. Another speculative possibility involves detecting the collective effect of planets in Andromeda through their influence on stellar motions. While we cannot detect individual planets' gravitational tugs on their stars at Andromeda's distance, future precision astrometry missions might potentially detect statistical signatures in the motions of large populations of stars that could be attributed to planet hosting. This would not tell us about specific planets, but could potentially confirm that planets exist in Andromeda and provide statistical information about their abundance and properties. These techniques remain at the edge of theoretical possibility, but the rapid pace of technological advancement in astronomy suggests that what seems impossible today might become routine within decades. Using Andromeda as a laboratory extends beyond simply observing it. Detailed computer simulations of galaxy formation and evolution use Andromeda as a key test case. Cosmological simulations start with the initial conditions present shortly after the Big Bang, when the universe was filled with nearly uniform gas with tiny density fluctuations imprinted by quantum processes during cosmic inflation. These simulations then calculate how gravity amplified those fluctuations over billions of years, causing gas to collapse into dark matter halos where galaxies formed. By comparing the simulated galaxies to real galaxies like Andromeda, astronomers can test whether our theoretical understanding of galaxy formation is correct. These simulations must incorporate many complex physical processes. They must model how gas cools and condenses to form stars, how massive stars explode as supernovae and inject energy back into the gas, how supermassive black holes grow and produce energetic feedback that affects galaxy evolution, how galaxies merge and interact gravitationally, and how gas flows into and out of galaxies. Getting all these processes right simultaneously is enormously challenging, requiring sophisticated computer codes running on the world's most powerful supercomputers. Andromeda serves as one of the most important observational benchmarks for these simulations. If a simulation produces a galaxy that matches Andromeda's properties, its mass, size, spiral structure, stellar populations, satellite system, merger history, and so on, then we gain confidence that the simulation is capturing the relevant physics correctly. Recent simulations have successfully reproduced many of Andromeda's observed properties, but discrepancies remain. For instance, simulations tend to produce too many satellite galaxies compared to observations, a problem called the missing satellites problem. Various solutions have been proposed, including that many satellite galaxies are too faint for current surveys to detect, or that the nature of dark matter differs from the simplest models in ways that suppress small-scale structure formation. Andromeda's actual satellite population provides crucial data for testing these ideas. Similarly, simulations struggle to reproduce the detailed structure of galactic disks, often producing disks that are too thick or have incorrect rotation properties. Comparing simulated galaxies to Andromeda's observed disk structure helps refine the models. The future of Andromeda research promises exciting developments as new observational capabilities come online. Several next-generation telescopes and space missions will dramatically improve our ability to study this neighboring galaxy. The James Webb Space Telescope, launched in December 2021, will observe Andromeda in infrared wavelengths with unprecedented sensitivity and resolution, potentially resolving individual stars across more of the galaxy than ever before, and detecting the faintest stellar populations. Webb's infrared capabilities will pierce through dust to reveal star formation occurring in obscured regions, and will detect cool brown dwarfs and old white dwarfs that are too faint for optical telescopes to see. Ground-based, extremely large telescopes currently under construction will revolutionize Andromeda studies. The Extremely Large Telescope in Chile, with a primary mirror 39 meters in diameter, will have collecting area and resolution far exceeding current facilities. It will be able to study individual stars in Andromeda with spectroscopy, determining their chemical compositions, ages, and radial velocities. This will allow detailed reconstruction of Andromeda's formation history by tracing how the abundance of heavy elements has evolved over time, and how stellar populations with different properties are distributed throughout the galaxy. The Giant Magellan Telescope and the 30-meter telescope, also under construction, will provide similar capabilities, ushering in an era where we can study individual stars in nearby galaxies, almost as well as we currently study stars in our own galaxy. Future space missions dedicated to astrometry will measure the precise positions and motions of stars in Andromeda with unprecedented accuracy. These measurements will allow astronomers to construct a three-dimensional map of stellar motions throughout the galaxy, revealing the detailed dynamics of its stellar populations. This will help answer questions about Andromeda's dark matter distribution, its merger history, and the mechanics of how spiral density waves propagate through its disk. The data will also allow much more precise predictions of exactly how the Andromeda Milky Way collision will unfold, including where our solar system might end up in the merged Andromeda Galaxy. Advanced gravitational wave detectors, while primarily designed to detect mergers of black holes and neutron stars, may eventually become sensitive enough to detect the gravitational waves that will be produced when Andromeda's and the Milky Way's supermassive black holes eventually merge billions of years from now. While we won't be around to observe that event directly, studying similar mergers in more distant galaxies will help us understand what to expect. Each new observational capability adds to our understanding, filling in details and answering questions while inevitably raising new mysteries that will require even more advanced observations to solve. The study of Andromeda also has philosophical dimensions that shouldn't be overlooked. When we look at this galaxy, we're seeing an enormous stellar system comparable to our own, containing hundreds of billions or trillions of worlds, each with its own story. Some of those worlds might harbor life. Some might host civilizations who look out at the universe with their own telescopes and wonder about their place in the cosmos. The vast majority of those potential civilizations are so far away that we could never communicate with them. Even if we could somehow send a signal at light speed toward Andromeda, it would take 2.5 million years to arrive, and another 2.5 million years for any reply to reach us. Any civilization we contacted would be separated from us, not just by distance, but by time itself, living in an epoch 5 million years removed from ours. This realization puts our own existence in perspective. We live in one galaxy among hundreds of billions in the observable universe. Our galaxy will eventually merge with Andromeda, just one of countless galaxy mergers occurring throughout the cosmos. Stars will continue forming, living their lives and dying. Planets will orbit those stars, some perhaps developing life and intelligence as happened on Earth. The universe will continue its grand evolution, moving inexorably from the hot, dense state following the Big Bang toward an increasingly cold, diffuse future as cosmic expansion continues and perhaps accelerates. In this vast cosmic context, the individual human lifespan seems infinitesimally brief, a mere flicker against the billions of years of galactic evolution. Yet this perspective, rather than diminishing the importance of human existence, can instead highlight its preciousness. We are, as far as we know, the only intelligent observers in our galaxy capable of understanding these cosmic processes, of piecing together the history of galaxies and stars, of predicting the future merger between Andromeda and the Milky Way billions of years hence. We can look at Andromeda and understand not just that it's a collection of stars, but that it represents 1 trillion separate suns, each with potentially its own family of worlds, its own story of birth, from collapsing gas clouds and eventual death in billions of years. We can comprehend that the light we see left those stars before our species existed, and travelled across a void so vast that it makes the scale of Earth, or even our solar system, seem insignificant. The ability to make these observations and draw these conclusions represents something remarkable in the universe's history. Atoms forged in the cores of ancient stars have organized themselves through the processes of chemistry and biology operating over billions of years on at least one planet, into structures capable of consciousness, of wonder, of understanding. We can look up at a faint smudge of light in the night sky and understand what it truly represents, can calculate its distance and mass, can predict when it will collide with our galaxy, can even speculate about whether anyone is looking back at us. This capacity for understanding seems sufficiently rare in the universe, perhaps unique to intelligent life, wherever it arises, that it represents something of genuine cosmic significance. Andromeda also reminds us of the dynamic nature of the cosmos. The universe is not static, but constantly evolving, with galaxies moving through space, colliding, merging, transforming. Stars are born, live, and die on timescales of millions to trillions of years. Planets form, evolve, and eventually are destroyed when their stars die. Everything we see in the night sky, including Andromeda, is a snapshot of an ongoing process that has been unfolding for nearly 14 billion years and will continue for an almost unimaginable duration into the future. Our observations capture a single moment in this vast temporal expanse, like a single frame from an epic film billions of years long. The inevitability of the Andromeda-Milky Way collision adds a certain poignancy to observations of our galactic neighbour. These two great stellar cities, each with their own complex histories of formation, growth through mergers, ongoing star formation, and evolving structure, are destined to become one. The merger will transform both galaxies irrevocably, erasing their spiral structures and mixing their stellar populations together into a new configuration that will persist for billions or trillions of years, until the universe has evolved so far beyond its current state that conditions may be entirely unlike anything we observe today. If humanity or our descendants, in whatever form they might take, still exist billions of years from now, they will witness this transformation firsthand, seeing Andromeda grow larger in the night sky over millions of years until it dominates the heavens, its structure becoming chaotic and distorted as tidal forces tear at both galaxies. Eventually, after multiple pass-throughs and billions of years of gradual settling, the residents of the merged Milky Galaxy will look up at a very different night sky than we see today. The Milky Way's band of light across the sky will be gone, replaced by a more uniform distribution of stars in an elliptical galaxy. The sky will likely be somewhat brighter on average, with more stars nearby due to the higher stellar density typical of elliptical galaxies. Satellite galaxies from both predecessor galaxies will orbit the merged system, and beyond them, other galaxies of the local group will still be visible, though the universe's accelerating expansion may have carried more distant galaxies beyond the observable horizon. It will be a different cosmos, transformed by the slow but inexorable working of gravity over billions of years. Studying Andromeda teaches us humility about our place in space and time, while simultaneously revealing the remarkable capability of human intelligence to understand the cosmos. We are tiny creatures on a small planet orbiting an ordinary star in a galaxy containing hundreds of billions of other stars. Our entire recorded history spans just a few thousand years, an eye blink against the timescales of galactic evolution. Yet despite these limitations, we've managed to measure the distance to Andromeda, determine its composition and structure, predict its future collision with our galaxy, and understand it as one example of the general phenomenon of spiral galaxy evolution occurring throughout the universe. This achievement, replicated in countless other areas of astronomy and science more broadly, demonstrates that intelligence, even when it arises in limited biological forms on a single planet, can nevertheless achieve genuine understanding of cosmic phenomena operating on scales that dwarf anything in our direct experience. As we look forward to future research on Andromeda, we can anticipate that each new observation will reveal additional complexity. This has been the pattern throughout the history of astronomy. Galileo's first telescopic observations revealed that there was far more to see than the naked eye could detect. Each improvement in telescope technology has unveiled new phenomena, new questions, new mysteries. When Hubble resolved Andromeda into individual stars, it wasn't the end of Andromeda studies, but the beginning of a new era where detailed analysis became possible. Similarly, upcoming facilities won't provide final answers, but will open new avenues of investigation, revealing details we cannot currently observe and raising questions we haven't yet thought to ask. The Andromeda Galaxy stands as a testament to the universe's grandeur, a trillion-sun stellar city floating in the cosmic void, approaching our own galaxy in a slow-motion cosmic dance that will culminate in merger billions of years hence. It serves as both a scientific laboratory where we can study galaxy evolution and test our theoretical models, and as a philosophical touchstone reminding us of the vast scales of space and time within which our brief existence unfolds. Every photon that reaches Earth from Andromeda carries information about stars and worlds separated from us by millions of light years, yet connected through the universal physical laws that govern all matter and energy. As long as humans continue looking up at the night sky with curiosity and wonder, Andromeda will remain one of our most important celestial neighbors, a source of endless fascination and a window into understanding galaxies, including our own Milky Way. In observing and studying this magnificent spiral galaxy, we participate in the universe's self-awareness, matter, and energy organized into forms capable of comprehending the cosmic context from which they emerged. This remains one of the most extraordinary facts about existence itself, worthy of the same wonder and awe that ancient observers felt when they first noticed that faint, mysterious patch of light among the stars. The story of how astronomers have pieced together our understanding of Andromeda represents one of humanity's greatest intellectual achievements, built upon centuries of painstaking observation, theoretical innovation, and technological advancement. In the centuries before Edwin Hubble's revolutionary distance measurement, astronomers wrestled with fundamental questions about the nature of nebulae. The German philosopher Immanuel Kant, in 1755, proposed what he called island universes, suggesting that some nebulae might be distant collections of stars comparable to our own stellar system. This was a remarkably prescient idea, proposed more than a century and a half before it could be confirmed observationally. Kant based his speculation on the appearance of certain nebulae, which showed an elliptical or disc-like shape reminiscent of what our Milky Way might look like if viewed from outside. However, speculation and proof are very different things in science. Throughout the 18th and 19th centuries, astronomers catalogued nebulae with increasing thoroughness. Charles Messier, a French astronomer searching for comets in the 1770s, compiled a list of fuzzy objects that might be mistaken for comets, but were actually fixed in position relative to the stars. His catalogue included 110 objects, with Andromeda listed as number 31, giving rise to its designation M31. Messier had no idea what these objects actually were. His primary goal was simply to help comet hunters avoid wasting time on objects that weren't comets. Yet his catalogue inadvertently created one of astronomy's most enduring reference systems, still widely used today. As telescopes improved throughout the 19th century, astronomers began classifying nebulae based on their appearance. Some showed a planetary disk-like shape and were called planetary nebulae, though they had nothing to do with planets. Others appeared as diffuse, irregular clouds. Still others, like Andromeda, showed a more organized structure, with what appeared to be spiral features extending from a central concentration. These spiral nebulae generated particular interest and controversy. Were they gas clouds within our galaxy? Perhaps solar systems in the process of formation, as some theorists suggested? Or were they, as Kant had speculated, distant stellar systems entirely separate from our Milky Way? The debate came to a head in the early 20th century as observational techniques improved. Spectroscopy, which splits light into its component wavelengths, revealed that different nebulae had very different spectral characteristics. True gaseous nebulae showed emission line spectra, with bright lines at specific wavelengths corresponding to excited atoms of hydrogen, oxygen, and other elements. Spiral nebulae, however, showed continuous spectra similar to stars, suggesting they were composed of stars rather than glowing gas. This was evidence in favor of the island universe hypothesis, but it wasn't conclusive. The nebulae might still be stellar associations within our galaxy. The Great Debate of 1920, formally titled The Scale of the Universe, brought these questions to a head. Harlow Shapley, who had recently revolutionized our understanding of the Milky Way's size and structure by studying globular clusters, argued that spiral nebulae were relatively nearby objects within our galaxy. His argument was partially based on observations of novae in Andromeda. Several star-like points of light had been observed to suddenly brighten in Andromeda, then fade over weeks or months. These were interpreted as novae, stellar explosions then thought to reach a fairly standard peak brightness. If this assumption was correct, the apparent brightness of these novae in Andromeda could be used to calculate its distance. The calculations suggested Andromeda was relatively nearby within the Milky Way system. Heber Curtis took the opposite position, arguing that spiral nebulae were distant island universes. He pointed to the fact that some spiral nebulae showed dark dust lanes silhouetted against their bright central regions, similar to what we might expect if we were viewing a disc-shaped stellar system, edge-on. He also noted that the novae observed in Andromeda, while mostly faint, were surprisingly numerous. If Andromeda were a relatively nearby nebula within our galaxy, the high frequency of novae would be difficult to explain. Curtis's interpretation was that Andromeda was far more distant than Shapley believed, making the novae appear faint despite being intrinsically bright. Both astronomers presented compelling cases, and the astronomical community remained divided. The resolution came not from philosophical arguments, but from direct measurement using a new technique. Henrietta Leavitt, working at Harvard College Observatory, had studied variable stars called Cepheids in the Magellanic Clouds, two small galaxies visible from the southern hemisphere that orbit our Milky Way. Leavitt discovered that Cepheid variables showed a precise relationship between their pulsation period and their intrinsic brightness. A Cepheid that pulsated with a period of, say, 10 days was intrinsically brighter than one with a 3-day period. This period luminosity relationship meant that by simply measuring a Cepheid's pulsation period, which could be done by observing how its brightness varied over time, you could determine its intrinsic brightness. Comparing this to its apparent brightness then gave the distance through basic geometry. Edwin Hubble, using the newly completed 100-inch Hooker telescope, searched Andromeda carefully for Cepheid variables. The telescope's unprecedented light-gathering power and resolution allowed him to detect individual stars in Andromeda's outer regions, something that had been impossible with smaller instruments. In 1923, he found what he was looking for: Cepheid variables pulsating with measurable periods. Applying Leavitt's period luminosity relationship, Hubble calculated that these Cepheids were extraordinarily far away, at least 900,000 light-years, far beyond any reasonable estimate of the Milky Way's size. The island universe hypothesis was confirmed. Andromeda was indeed a separate galaxy. The announcement fundamentally changed humanity's understanding of the cosmos. The Milky Way, previously thought to encompass the entire universe, was revealed as merely one galaxy among many. This discovery paralleled earlier paradigm shifts like the Copernican revolution that displaced Earth from the center of the solar system, or Hubble's later discovery that the universe itself is expanding, showing that galaxies are rushing away from each other in the aftermath of the Big Bang. Each of these discoveries reduced humanity's sense of cosmic centrality while simultaneously expanding our knowledge of the true scale and nature of existence. Modern distance measurements to Andromeda have refined Hubble's initial estimate upward to about 2.5 million light-years, nearly 3 times his original calculation. The revision came from better calibration of the period luminosity relationship and the recognition that there are actually 2 types of Cepheid variables with different properties. But Hubble's fundamental conclusion remained sound. Andromeda is a separate galaxy at an enormous distance from the Milky Way. This distance measurement opened the door to understanding Andromeda's true properties. If you know how far away something is and how bright it appears, you can calculate its intrinsic luminosity. If you can measure its angular size and know its distance, you can calculate its actual physical size. Suddenly, Andromeda transformed from a mysterious nebula into a measurable object whose properties could be determined quantitatively. The realization that Andromeda is approaching us rather than receding added another dramatic element to the story. In the 1910s and 1920s, Vesto Slipher at Lowell Observatory had measured the radial velocities of spiral nebulae by analyzing the Doppler shift of spectral lines in their light. Most nebulae showed redshifted spectra, indicating motion away from Earth. This observation would later become crucial evidence for the expanding universe. However, Andromeda showed a blue shift, indicating approach at about 300 kilometers per second. When corrected for the Sun's motion around the Milky Way and the Milky Way's own motion through space, this translated to Andromeda and the Milky Way approaching each other at roughly 110 kilometers per second. At first, this approaching motion might seem to contradict the universal expansion that carries distant galaxies away from us. However, there's no contradiction. The expansion of the universe manifests primarily on very large scales, between galaxy clusters separated by hundreds of millions or billions of light years. On smaller scales, local gravitational effects dominate. Within galaxy groups and clusters, galaxies can and do move toward each other under mutual gravitational attraction. The local group, containing the Milky Way, Andromeda, and several dozen smaller galaxies, is gravitationally bound, meaning its members orbit their common center of mass, rather than participating in the cosmic expansion. Andromeda and the Milky Way, as the two most massive members of the local group, dominate its gravitational dynamics and are falling toward each other under their mutual attraction. Understanding the future collision between these galaxies requires sophisticated computer simulations that model how gravitational forces between millions or billions of particles, representing stars, gas clouds, and dark matter, evolve over time. Early simulations, performed beginning in the 1970s as computers became powerful enough to handle such calculations, showed that galaxy collisions were far more complex than simple mergers where two objects come together and stick. Instead, galaxies interpenetrate, pass through each other, separate again, then fall back together for subsequent encounters. Each pass-through distorts both galaxies through tidal forces, pulling stars and gas into long streams extending far into space. These tidal tails, observed in many colliding galaxies throughout the universe, can stretch for hundreds of thousands of light years, far beyond the galaxy's original boundaries. Modern simulations of the Andromeda-Milky Way collision incorporate data about both galaxies' masses, sizes, shapes, rotation rates, and current relative velocity. They also include the substantial populations of satellite galaxies orbiting each major galaxy, since these smaller systems will participate in the collision as well, adding complexity to the gravitational interactions. The simulations show that the first close approach will occur in approximately 4.5 billion years, though this figure has uncertainties of several hundred million years depending on exact assumptions about the galaxy's masses and current motions. During this first approach, the galaxies will pass through each other, with their disks interpenetrating. The gravitational interaction will distort both galaxies significantly, sending streams of stars arcing out into space and triggering intense star formation as gas clouds collide and compress. After the first pass-through, the galaxies will separate again, moving apart as their mutual motion carries them past each other. However, they won't escape. The gravitational attraction between them will slow their separation, eventually halt it, and pull them back together for a second encounter. This second pass will be even more disruptive than the first because the galaxy's relative velocity will be lower, giving gravity more time to work its effects. Multiple subsequent encounters will follow, each stripping away more of the galaxy's organized structure, until finally, after perhaps a dozen passes over 2 billion years or so, the two galaxies' cores merge and the stars settle into a new configuration. The final product, Milkomeda, will probably be a giant elliptical galaxy. Elliptical galaxies lack the spiral structure and flattened disk of spiral galaxies. Instead, their stars occupy a more three-dimensional ellipsoidal distribution. Ellipticals range from nearly spherical to quite elongated, like footballs. They generally contain older stellar populations with little ongoing star formation, having exhausted most of their gas in ancient starbursts or lost it through various processes. The merger between Andromeda and the Milky Way will likely consume most of the gas in both galaxies in a tremendous starburst triggered by the collision, creating millions or billions of new stars in a relatively brief period. After this burst of activity, Milky will settle into a more quiescent state, with little star formation, slowly evolving as its stars age. What will happen to Earth and the solar system during this cosmic catastrophe? The answer depends on many factors and involves substantial uncertainty. Our first concern might be whether the Sun will collide with another star during the merger. Fortunately, despite the violence of galaxy collisions, direct stellar collisions are almost impossibly rare. Consider that the Sun has a diameter of about 1.4 million kilometers, while the distance to the nearest star is about 40 trillion kilometers. If you scale the Sun down to the size of a basketball, the nearest star would be another basketball about 6,000 kilometers away. The space between stars is almost entirely empty, so even when two galaxies' worth of stars interpenetrate, the chance that any two stars will actually hit each other is negligible. It's like throwing two swarms of gnats at each other. The gnats will pass through both swarms with almost no collisions despite the apparent chaos. However, even though stellar collisions won't occur, the solar system could still be affected by gravitational perturbations during close encounters with passing stars. If another star passes within a few light years of the Sun, its gravity could perturb the orbits of planets, particularly the outer planets, or disturb the Oort cloud, the spherical shell of comets surrounding the solar system at distances of thousands of astronomical units. Such perturbations might send a shower of comets into the inner solar system, potentially increasing impact hazards for Earth. More dramatically, if a star passes particularly close, it might even eject planets from the solar system entirely, sending them wandering through space unbound to any star. An even more significant effect involves the solar system's overall location in the merged galaxy. Currently, the Sun orbits about 26,000 light-years from the Milky Way's center, in a relatively sparse region of the galactic disk. During the merger, the chaotic gravitational interactions could fling the solar system to a very different location. We might end up much closer to the center of Milky, in a region with higher stellar density. Alternatively, we could be ejected from the disk entirely, sent into the galactic halo, or even into intergalactic space. Computer simulations suggest that a substantial fraction of stars in both galaxies, perhaps 10 to 20%, will be ejected into the halo or beyond during the merger. If this happens to the solar system, the night sky would look very different, with far fewer nearby stars and the galactic disk visible as a distant concentration of light rather than the Milky Way band we currently see. Of course, these concerns about Earth's fate during the galactic merger may be moot. The Sun is currently about 4.6 billion years old, approximately halfway through its main sequence lifetime. In another 5 billion years or so, the Sun will exhaust the hydrogen in its core and begin evolving off the main sequence into a red giant star. As it does so, it will swell enormously, potentially expanding beyond Earth's current orbit. Even if Earth isn't physically engulfed, the increased solar radiation will make the planet uninhabitable long before, probably within 1 to 2 billion years. The oceans will evaporate, the atmosphere will be stripped away, and Earth will become a lifeless, scorched rock. This solar evolution will occur around the same time as the galactic merger begins, meaning that Earth's doom is likely sealed by stellar evolution before galactic dynamics become relevant. Still, the merger matters enormously for any life in either galaxy. If there are other civilizations on planets orbiting other stars in Andromeda or the Milky Way, they'll face the same challenges we would. Advanced civilizations might be capable of moving their planets to safer orbits, or abandoning planets entirely for artificial habitats that can be relocated as needed. It's fascinating to speculate whether any civilizations in either galaxy might be making preparations now for the collision. Billions of years hence, whether they're mapping safe zones where stellar densities will remain low and gravitational perturbations minimal, or whether they're simply accepting that their descendants, if any exist so far in the future, will deal with challenges in their own time with technologies we cannot imagine. The satellite galaxies orbiting Andromeda add layers of complexity to both the galaxy's current structure and its future evolution. These smaller galaxies range from relatively substantial systems like M32, which contains hundreds of millions of stars and shows some ongoing star formation, to ultra-faint dwarfs discovered only in recent years through careful analysis of deep sky surveys. These ultra-faint dwarfs contain as few as a few thousand stars spread over volumes hundreds of light-years across, making them incredibly diffuse and difficult to detect. They're visible at all only because their stars, while few in number, are gravitationally bound and moving together through space, creating a subtle overdensity against the background of unrelated foreground and background stars. M32, the brightest of Andromeda's satellites, is itself a peculiar object. Despite being classified as a dwarf elliptical galaxy, it shows signs of having once been much larger. Some astronomers believe M32 is the stripped core of a once substantial galaxy that passed too close to Andromeda and had its outer regions torn away by tidal forces, leaving only the dense central region we see today. The stars stripped from M32 would now be distributed throughout Andromeda's halo, indistinguishable from stars born in Andromeda itself or accreted from other satellites. This process of tidal stripping is common in galaxy groups and clusters, with smaller galaxies gradually losing mass to their larger neighbours over billions of years. M110, the other bright satellite, is a more typical dwarf elliptical galaxy, though still quite substantial with several billion stars. It shows evidence of past star formation activity more recent than typically seen in elliptical galaxies, with some stars that formed only a few 100 million years ago. This suggests M110 contained gas relatively recently in cosmic terms and was forming stars until some process, possibly ram pressure stripping as it moved through Andromeda's hot gaseous halo, removed the remaining gas and shut down star formation. The galaxy now appears to be evolving passively, with no new stars forming, and the existing stellar population slowly aging. Beyond these two bright satellites, Andromeda's retinue includes numerous fainter dwarfs. Some are dwarf spheroidal galaxies, diffuse systems containing primarily old stars with little or no gas or recent star formation. Others are dwarf irregular galaxies, smaller and less organized than typical spirals or ellipticals, but containing some gas and ongoing star formation. Each of these satellites has its own individual history, its own story of formation and evolution, though that history is increasingly dominated by interaction with Andromeda as they orbit the larger galaxy. Eventually, most or all of these satellites will be consumed by Andromeda, their stars added to the larger galaxy's halo population, their individual identities erased by the inexorable working of gravity over billions of years. The distribution and properties of Andromeda's satellite galaxies provide crucial tests for cosmological models and our understanding of dark matter. In the standard cosmological model, based on cold dark matter and dark energy, structure formation proceeds hierarchically. Small dark matter halos form first, then merge to build progressively larger halos. Galaxies form within these halos, and galaxy properties depend largely on the dark matter, halo's mass and merger history. This model predicts that large galaxies like Andromeda should be surrounded by numerous dark matter subhalos, the remnants of smaller halos that merged with the main halo but retained some individual identity. Some of these subhalos should contain visible galaxies, which we observe as satellite systems like those around Andromeda. However, there's a significant discrepancy between predictions and observations. Simulations predict that halos like Andromeda's should contain hundreds or even thousands of substantial subhalos, yet we observe only a few dozen satellite galaxies. This is the missing satellites problem mentioned earlier. Various solutions have been proposed. Perhaps most satellite halos are too small to form stars, remaining dark and therefore undetectable. Perhaps star formation is suppressed in small halos by various feedback processes, such as ultraviolet radiation from the first generation of stars ionizing the universe and heating gas too much for it to collapse into small galaxies. Or perhaps the properties of dark matter differ from simple models in ways that suppress small-scale structure. Observations of Andromeda's satellites help constrain these possibilities. Deep surveys searching for ultra-faint satellites have found several in recent years, suggesting that many satellites likely remain undiscovered. Each new discovery slightly reduces the discrepancy between predictions and observations. However, it remains unclear whether enough faint satellites exist to fully resolve the problem. Future surveys, going deeper and covering more of the sky around Andromeda, will continue searching for these faint systems. The results will either find enough satellites to match predictions, supporting current models, or maintain the discrepancy, potentially requiring modifications to our understanding of dark matter or galaxy formation. The dark matter halo surrounding Andromeda, extending far beyond the visible galaxy, represents most of the system's total mass. This invisible component reveals itself through its gravitational effects on visible matter. When astronomers measure how fast stars and gas orbit at various distances from Andromeda's center, they find that orbital velocities remain roughly constant, or even increase slightly, even in the far outer regions of the galaxy. According to Newtonian gravity, if most of the galaxy's mass were concentrated in the visible stars and gas, orbital velocities should decrease with distance from the center, just as outer planets in our solar system orbit more slowly than inner planets. The observed flat or rising rotation curve indicates that significant mass exists beyond the visible galaxy, distributed in an extended halo. Estimates suggest Andromeda's dark matter halo extends at least 1 million light-years from the galaxy's center, possibly much farther, and contains several times more mass than all the visible stars, gas, and dust combined. The halo's total mass is estimated at around 1.5 trillion solar masses, compared to perhaps 200 to 400 billion solar masses in visible matter. This means dark matter constitutes roughly 80 to 85% of Andromeda's total mass, consistent with the universal ratio found throughout the cosmos. The halo's density decreases with distance from the center, following a profile that simulations predict. Dark matter halos should have based on how they form through gravitational collapse in an expanding universe. The nature of this dark matter remains one of physics' deepest mysteries. We know it doesn't interact with light, making it invisible to all electromagnetic observations. It doesn't appear to interact significantly with normal matter, except through gravity. It doesn't collapse into dense structures like stars or planets, suggesting it doesn't radiate energy efficiently and cool down as normal matter does. Beyond these negative statements, we know remarkably little about what dark matter actually is. The leading hypothesis suggests it consists of new types of subatomic particles beyond those described by the standard model of particle physics. various candidates have been proposed, including WIMPs, which would be heavy particles that interact only weakly with normal matter, and axions, which would be much lighter particles produced in vast numbers in the early universe. Despite decades of searching, no dark matter particle has been definitively detected in laboratory experiments. Massive underground detectors watch for the rare occasions when dark matter particles might collide with atomic nuclei, producing tiny flashes of light or small amounts of ionization. Particle colliders like the Large Hadron Collider search for evidence of dark matter particles being created in high-energy collisions. So far, these searches have come up empty, though they've ruled out various specific models and parameter ranges. The gravitational evidence for dark matter's existence is overwhelming. We see its effects in galaxy rotation curves like Andromeda's, in the motions of galaxies within clusters, in gravitational lensing observations, and in the cosmic microwave background radiation left over from the Big Bang. Yet the particles themselves remain frustratingly elusive. Alternative theories have been proposed that modify our understanding of gravity rather than invoking new particles. Modified Newtonian dynamics, or MOND, suggests that gravitational physics works differently at very low accelerations than Newton's and Einstein's theories predict. In this framework, the flat rotation curves of galaxies result from modified gravity rather than dark matter. MOND can successfully explain many galactic rotation curves with surprisingly few parameters. However, it struggles to explain observations on larger scales, such as galaxy cluster dynamics and cosmic microwave background patterns, without invoking some dark matter anyway. Most physicists currently favor the dark matter particle hypothesis over modified gravity, but the question remains open pending direct detection of dark matter particles, or successful alternative theories that match all observations. Andromeda's central supermassive black hole exemplifies a class of objects that fundamentally shape galaxy evolution. Nearly all large galaxies contain supermassive black holes at their centers, with masses ranging from millions to billions of times the Sun's mass. These black holes grow through two primary mechanisms: accretion of gas and dust from their surroundings, and mergers with other black holes during galaxy collisions. The relationship between black hole mass and various galaxy properties, particularly the mass of the central bulge, suggests a deep connection between black hole growth and galaxy evolution, though the details of this connection remain debated. When gas falls toward a supermassive black hole, it doesn't plunge directly in. Angular momentum causes the gas to form an accretion disk, a swirling disk of material spiraling slowly inward. Friction within the disk heats it to tremendous temperatures, sometimes millions of degrees, causing it to emit enormous amounts of radiation across the electromagnetic spectrum. In the most extreme cases, active galactic nuclei, or AGN, the central black hole outshines the entire rest of the galaxy combined, with the tiny accretion disk producing more light than hundreds of billions of stars. Andromeda's central black hole is currently not very active, accreting only small amounts of material and producing relatively little radiation. However, it was likely much more active in the past, and will become active again during the merger with the Milky Way when large amounts of gas are funneled toward the center. The energy released by active galactic nuclei can have profound effects on their host galaxies. Powerful jets of particles accelerated near the black hole can extend for millions of light years, plowing into the surrounding gas and heating it. This AGN feedback can regulate star formation by heating gas too much for it to collapse and form stars, or by expelling gas from the galaxy entirely. This feedback may explain why massive galaxies tend to have low star formation rates despite containing large amounts of gas. The black hole's feedback regulates the gas supply, preventing runaway star formation. The balance between gas cooling and collapsing to form stars, and feedback heating gas and driving it out, determines how galaxies evolve over cosmic time. When Andromeda and the Milky Way eventually merge, their central supermassive black holes will spiral together and merge as well. The merger will release enormous amounts of energy in the form of gravitational waves, ripples in space-time itself, predicted by Einstein's general relativity and directly detected for the first time in 2015 from merging stellar mass black holes. Supermassive black hole mergers produce gravitational waves at much lower frequencies than stellar mass mergers, frequencies that ground-based detectors like LIGO cannot access. However, future space-based detectors like LISA, the Laser Interferometer Space Antenna, may be able to detect supermassive black hole mergers throughout the universe, providing a completely new window on galaxy evolution and testing general relativity in the most extreme gravitational environments. The eventual merger of Andromeda's and the Milky Way's black holes will create a single black hole with a mass of roughly 110 to 210 million solar masses, the sum of the two progenitors. This new black hole will settle into the center of Milkomeda, where it may continue growing slowly by accreting gas and occasionally consuming stars that wander too close. Over trillions of years, as stars in Milkomeda age and die, the central black hole will likely be the longest-lived object in the galaxy, persisting long after the last stars burn out and the galaxy becomes a collection of cold stellar remnants, white dwarfs, neutron stars, and black holes orbiting in the darkness. Star formation regions in Andromeda's spiral arms offer glimpses of the stellar birth process in action. These regions appear as bright knots and patches in photographs, particularly prominent in ultraviolet images that highlight hot young stars. The process begins when giant molecular clouds, vast accumulations of cold molecular hydrogen, sometimes hundreds of light years across and containing hundreds of thousands or millions of solar masses of gas, become gravitationally unstable and begin collapsing. The exact trigger for collapse varies. Sometimes it's the passage of a spiral density wave compressing the cloud. Other times it's a nearby supernova, whose expanding shockwave compresses surrounding gas. Once collapse begins, the cloud fragments into smaller clumps, each collapsing independently. As a gas clump collapses, it heats up as gravitational potential energy converts to thermal energy. The increasing density and temperature eventually trigger nuclear fusion in the core, where hydrogen nuclei overcome their mutual electrical repulsion and fuse to form helium, releasing energy in the process. A star is born. The most massive stars, those exceeding about 25 times the Sun's mass, are extremely luminous and hot, with surface temperatures above 25,000 degrees Kelvin. These O and B-type stars emit most of their energy in the ultraviolet, making them prominent in UV observations despite being relatively rare. They live only a few million years before exhausting their nuclear fuel and exploding as supernovae. The supernova explosions inject energy back into the surrounding gas, heating it and driving it away from the star. Star-forming region. They also enrich the gas with heavy elements synthesized during the star's life and in the explosion itself. Oxygen, carbon, iron, and all the other elements heavier than helium that make up planets and living things are created in stars and dispersed by supernovae. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen you breathe was forged in the core of a star that exploded billions of years ago. Its material eventually incorporated into the cloud from which our solar system formed. Andromeda's star-forming regions are creating new generations of stars that will enrich the galaxy with heavy elements just as previous generations have done, continuing the cycle of stellar birth, life, death, and rebirth that has been ongoing since the first stars formed in the early universe. The rate of star formation in Andromeda, approximately 1 solar mass per year, might seem insignificant compared to the galaxy's total stellar mass of several hundred billion solar masses. However, integrated over billions of years, this steady rate has built up the enormous stellar population we observe today. Andromeda's star formation rate has varied over its history. When the galaxy first formed, probably through the merger of several smaller proto-galaxies, star formation rates were likely much higher, possibly tens or hundreds of solar masses per year. As the galaxy evolved and exhausted or expelled much of its gas, star formation rates declined to the current more sedate level. During the upcoming merger with the Milky Way, star formation will spike dramatically as colliding gas clouds trigger intense bursts of star formation, possibly reaching rates of hundreds of solar masses per year. After the merger, once most of the gas is consumed or expelled, star formation will decline to very low levels, and Milky will passively evolve as an elliptical galaxy with minimal ongoing star formation. The mysterious double nucleus at Andromeda's center continues to intrigue astronomers decades after its discovery. The initially puzzling appearance of two bright concentrations of light at the galaxy's center was eventually explained through detailed modeling of stellar dynamics, combined with high-resolution observations. The true galactic center, marked by the supermassive black hole's position, coincides with one of the bright concentrations. The other concentration is actually a disk of old red stars orbiting the black hole with a radius of about 5 light-years. We see this disk nearly edge on from our vantage point, making it appear as a distinct bright spot rather than spread out across the sky as it would if we viewed it face-on. This eccentric stellar disk likely formed from stars captured from a smaller galaxy that merged with Andromeda in the past. When a small galaxy falls into a larger one, the smaller galaxy's core can survive for a significant time, orbiting within the larger galaxy's potential well. Over hundreds of millions or billions of years, dynamical friction gradually causes the infalling core to sink toward the center. If the infalling galaxy's black hole survives to the center and merges with the central black hole, the captured stars can form a disk orbiting the merged black hole. The orientation of this disk depends on the orbital parameters of the original merger, explaining why we observe it nearly edge-on. The double nucleus structure provides important clues about Andromeda's merger history. It indicates at least one significant merger occurred in the relatively recent past, probably within the last few billion years. This conclusion is supported by other evidence of past mergers, including the stellar streams in the halo and the peculiar properties of some satellite galaxies. Taken together, this evidence paints a picture of Andromeda as a galaxy built through hierarchical merging, growing to its current large size by consuming numerous smaller neighbors over cosmic time. This growth through mergers is a fundamental prediction of cosmological models and appears to be the primary way that large galaxies like Andromeda form and evolve. The stellar streams in Andromeda's halo serve as fossil records of these ancient merger events. When astronomers map the distribution of stars in the halo with sufficient detail, they find that the distribution is not smooth, but shows clumps, streams, and overdensities. Each of these structures represents the torn-apart remnants of a satellite galaxy that Andromeda consumed. The giant southern stream, one of the most prominent features, extends for hundreds of thousands of light-years across the southern portion of Andromeda's halo. It contains stars with similar properties, ages, compositions, and velocities, indicating they originated from a single progenitor galaxy. By studying the stream's properties, astronomers can reconstruct the characteristics of the original galaxy and approximately when it was disrupted. Similarly, other streams and clumps in the halo each tell their own stories. The northeast shelf appears to be a more recent merger, with the progenitor galaxy possibly still identifiable as one of Andromeda's current satellites in the process of being tidally disrupted. By cataloguing all these features and modelling their dynamics, astronomers are reconstructing Andromeda's merger history in remarkable detail. This work is painstaking, requiring extremely deep observations to detect the faint halo stars and sophisticated analysis to separate distinct structures from the background stellar population. However, the scientific rewards are substantial. Understanding how Andromeda grew through mergers helps us understand galaxy formation more generally, since all large galaxies likely grew through similar processes. The rotation mysteries in Andromeda's outer regions highlight how complex real galaxies are compared to idealized models. In the simplest picture, a spiral galaxy is a rotating disk with all stars orbiting in the same direction and plane. Reality is messier. Andromeda shows evidence of counter-rotating stellar populations, where some stars orbit opposite to the galaxy's overall rotation direction. It shows warping, where the disk plane tilts at different angles at different distances from the center. It shows the massive rotating disk of stars extending far beyond the bright spiral arms. All these features reflect the galaxy's complex formation history, with different components added at different times through different processes. The extended rotating disk in Andromeda's outer regions is particularly intriguing. This disk contains a substantial fraction of the galaxy's stellar mass, but extends beyond the prominent spiral structure visible in most images. It rotates more slowly than the inner disk and contains primarily older, redder stars. The disk's existence suggests that Andromeda has grown significantly over time, either through mergers that added stars to the outer regions, or through redistribution of stars originally in the inner galaxy, outward through various dynamical processes. Distinguishing between these scenarios requires detailed modeling and comparison with simulations, work that continues today as astronomers try to understand the full picture of how Andromeda formed and evolved. For observers on Earth, Andromeda represents our most accessible view of a large spiral galaxy. Its relative proximity, just 2.5 million light-years, means we can resolve individual bright stars across much of the galaxy using modern telescopes. This allows studies that would be impossible for more distant galaxies, where even the brightest stars blur together. The Hubble Space Telescope's panchromatic Hubble Andromeda Treasury project imaged large swaths of Andromeda's disk, resolving over 100 million individual stars. This dataset allows astronomers to study stellar populations in unprecedented detail, mapping how star ages, compositions, and formation histories vary across the galaxy. This information provides crucial insights into how spiral galaxies like Andromeda assemble and evolve over billions of years. The PHAT survey, as it's commonly called, revealed structure and complexity that couldn't be seen in earlier lower resolution observations. By resolving individual stars, astronomers could separate younger blue stars from older red stars, Map the detailed structure of spiral arms, identify star clusters ranging from young open clusters to ancient globular clusters, and trace the galaxy's star formation history across different regions. The survey found that star formation in Andromeda hasn't been uniform across the disk. Some regions show evidence of recent bursts of star formation, while others have been relatively quiescent for hundreds of millions of years. These variations reflect local conditions in the interstellar medium, including gas density, turbulence, and perhaps triggering events like spiral density waves or past merger-induced disturbances. One surprising finding from detailed studies of Andromeda's stellar populations is that the galaxy appears to have experienced a major burst of star formation roughly 2 to 4 billion years ago. During this period, star formation rates were significantly higher than today, possibly triggered by a merger with another galaxy. This ancient starburst created a large population of stars that are now middle-aged, having evolved off the main sequence into red giant stars. These stars contribute significantly to Andromeda's luminosity and give parts of the galaxy a characteristic reddish color. The cause of this ancient starburst remains debated, but it likely involved either a gas-rich merger that brought fresh fuel for star formation, or strong tidal interactions with another galaxy that compressed gas clouds and triggered collapse. The ability to see Andromeda with the naked eye connects modern observers with ancient peoples who watched the same galaxy thousands of years ago. The photons entering your eye when you observe Andromeda departed from stars in that galaxy 2.5 million years ago. But the human brain perceiving those photons represents an evolutionary lineage stretching back billions of years. The atoms composing your body were forged in stars similar to those in Andromeda, through the same nuclear fusion processes operating throughout the universe. In a very real sense, we are made of star stuff, to use Carl Sagan's evocative phrase, and when we observe Andromeda, we're witnessing our cosmic origins played out on galactic scales. For amateur astronomers, observing Andromeda offers rewards ranging from the simple thrill of seeing another galaxy with your own eyes to the satisfaction of photographing its intricate structure. On a dark night far from city lights, locate the constellation Andromeda by finding the Great Square of Pegasus and following the line of stars extending from one corner. About halfway along this line, a faint fuzzy patch marks the galaxy's location. With the naked eye, you'll see only the bright central core, but that's enough to know you're seeing light from 1 trillion suns across an intergalactic gulf. Binoculars expand the view, showing the galaxy's elongated shape and hinting at structure within it. Through a small telescope, perhaps 4 to 6 inches in aperture, the dust lanes become visible as dark streaks crossing the galaxy's disk, and the two bright satellite galaxies M32 and M110 appear as small fuzzy patches nearby. Larger amateur telescopes, especially those in the 10 to 16-inch range, can reveal more detailed structure under dark skies. The spiral arms begin to show, appearing as subtle variations in brightness extending from the central bulge. Some of the brighter globular clusters orbiting Andromeda become visible as tiny fuzzy stars. With careful observation and averted vision, using your peripheral vision, which is more sensitive to faint light than the center of your visual field, you can trace the galaxy's extent across several degrees of sky, roughly 5 or 6 times the width of the full moon. This reveals Andromeda's true enormous size, though most of its light comes from the central regions that appear brightest. Astrophotography reveals even more spectacular views. Modern digital cameras, particularly those designed for astrophotography with cooled sensors to reduce noise, can capture stunning images of Andromeda with relatively modest equipment. A good camera attached to a tracking mount to compensate for Earth's rotation, combined with a telephoto lens or small telescope, can photograph Andromeda, showing detail competitive with professional images from decades past. Long exposures, ranging from minutes to hours when multiple shorter exposures are combined, reveal faint outer regions and subtle color variations reflecting different stellar populations. The galaxy's overall bluish tint in the spiral arms contrasts with the yellowish central bulge, while the dark dust lanes stand out prominently. Professional observatories studying Andromeda employ instruments across the electromagnetic spectrum, each revealing different aspects of the galaxy's nature. Radio telescopes observe the 21-centimeter line from neutral hydrogen, mapping the distribution and kinematics of cold gas throughout the galaxy. These observations show that Andromeda contains roughly 5 billion solar masses of neutral hydrogen, distributed primarily in a ring extending from about 30,000 to 90,000 light-years from the center. The gas shows complex motions beyond simple rotation, including radial flows and vertical motions that reflect the galaxy's dynamical complexity. Radio observations also detect molecular clouds, where star formation occurs by observing emission from carbon monoxide molecules, which trace regions of dense molecular hydrogen. Infrared observatories like NASA's Spitzer Space Telescope and the European Space Agency's Herschel Space Observatory have mapped Andromeda's dust in unprecedented detail. These observations reveal intricate structures in the dust distribution, including dust lanes, spiral features, and rings. The dust is not uniformly distributed, but concentrated in specific regions, particularly along the spiral arms where it's associated with star formation. Warm dust heated by young stars glows at mid-infrared wavelengths around 20 to 30 microns, while cooler dust pervading much of the galaxy emits at far infrared wavelengths beyond 100 microns. By measuring dust temperatures and masses across the galaxy, astronomers can understand how dust is created in stellar atmospheres and supernova explosions, how it's distributed by stellar winds and galactic dynamics, and how it affects star formation by shielding gas from ultraviolet radiation and facilitating cooling that allows clouds to collapse. Ultraviolet observations from satellites like NASA's Galaxy Evolution Explorer, highlight Andromeda's youngest stellar populations. Massive stars with surface temperatures exceeding 15,000 to 20,000 degrees. Kelvin emit most of their light in the ultraviolet, making them prominent in UV images despite their rarity. Galax images of Andromeda show the spiral arms outlined in brilliant blue-white, tracing recent star formation. By comparing UV emission with other traces of star formation like hydrogen alpha emission from ionized gas, astronomers can measure star formation rates across the galaxy and understand how star formation efficiency varies with local conditions like gas density and the strength of spiral density waves. X-ray observations from telescopes like NASA's Chandra X-ray Observatory and the European XMM Newton satellite detect the most energetic phenomena in Andromeda. X-ray binary systems, where a neutron star or black hole accretes material from a companion star, emit copious X-rays as the infalling material heats to millions of degrees. Chandra has identified hundreds of X-ray sources in Andromeda, including both high-mass X-ray binaries with massive stellar companions and low-mass X-ray binaries with sun-like companions. Supernova remnants also emit X-rays as their expanding shockwaves plow through surrounding gas. The hot gas in Andromeda's halo produces diffuse X-ray emission that traces its temperature and density distribution. The central black hole occasionally flares in X-rays when it accretes small amounts of gas. providing opportunities to study accretion physics in relatively low luminosity active galactic nuclei. Gamma-ray observations from NASA's Fermi Gamma-ray Space Telescope detect the highest energy photons coming from Andromeda. These observations reveal emission from cosmic ray interactions with gas and starlight throughout the galaxy. Cosmic rays, energetic particles accelerated by supernova shocks and other violent processes, pervade the galaxy and occasionally collide with gas atoms or photons, producing gamma rays through various interactions. The gamma-ray emission traces where cosmic rays are most abundant and provides information about these energetic particles that's difficult to obtain through other means. Surprisingly, Fermi detected more gamma-ray emission from Andromeda than expected, based on the galaxy's star formation rate, suggesting either that cosmic ray production is more efficient in Andromeda than in our galaxy, or that cosmic rays are confined more effectively, increasing their interaction rates with gas and photons. Multi-wavelength observations combined provide a comprehensive view of Andromeda as a complex astrophysical system. The visible light shows primarily stars. Infrared reveals dust and cooler stellar populations. Ultraviolet highlights hot young stars. X-rays expose compact objects and hot gas. Radio traces cold gas and magnetic fields. Gamma rays indicate cosmic ray interactions. Each wavelength adds information that couldn't be obtained from any other. And synthesizing all this data creates an understanding far richer than any single wavelength could provide. This multi-wavelength approach has become standard in modern astronomy, with major surveys often coordinated across multiple observatories to ensure comprehensive coverage of important targets like Andromeda. The question of planets in Andromeda, while currently beyond direct observational reach, invites fascinating speculation grounded in what we've learned about planetary systems in our own galaxy. The detection of thousands of exoplanets over the past 3 decades has revealed that planet formation is a natural outcome of star formation, occurring around the vast majority of stars regardless of stellar type. Rocky planets form through the gradual accumulation of solid material in protoplanetary disks, while gas giants form either through similar core accretion, followed by rapid gas accumulation, or through direct gravitational instability in massive disks. The diversity of exoplanets we've discovered suggests that planetary systems can have radically different architectures from our own solar system, shaped by initial disk conditions and subsequent dynamical evolution. Extrapolating these findings to Andromeda leads to staggering numbers. With approximately 1 trillion stars, even conservative estimates suggest Andromeda hosts at least 1 trillion planets total, possibly several trillion. If most stars have multiple planets, as appears common in our galaxy. Of these trillions of worlds, perhaps 10 to 20% orbit in their stars' habitable zones, where temperatures could allow liquid water on planetary surfaces. This suggests 100 to 200 billion potentially habitable worlds in Andromeda alone. Some fraction of these might actually host life, though the probability of life arising on any given habitable world remains deeply uncertain. Even if only 1 in a million habitable worlds develops life, that still implies hundreds of thousands of living worlds in Andromeda. The possibility of intelligent life and technological civilizations in Andromeda raises even more speculative questions. If we assume life arises relatively commonly on suitable worlds, and that some fraction of life-bearing worlds eventually develop intelligence and technology, then Andromeda might host multiple technological civilizations at any given time. However, enormous uncertainties plague such estimates. We don't know how likely life is to arise given suitable conditions. We don't know how likely simple life is to evolve into complex multicellular life. We don't know how likely intelligence is to arise, or how likely technological civilizations are to survive for substantial periods without self-destruction or stagnation. The famous Fermi paradox asks why, if intelligent life is common, we see no evidence of it. Perhaps intelligent life is extremely rare. Perhaps it's common, but technological civilizations are short-lived. Perhaps interstellar communication or travel is more difficult than we imagine. Perhaps we simply don't know what to look for. The possibility that other civilizations exist in Andromeda, perhaps looking back at the Milky Way with their own telescopes and wondering if anyone is here, captures the imagination powerfully. If such civilizations exist, they face the same fundamental challenges we do: understanding their place in the universe, grappling with the knowledge of their galaxy's eventual collision with ours, perhaps wondering whether life exists elsewhere. They would study the Milky Way as we study Andromeda, possibly reaching similar conclusions about galactic structure, stellar populations, and cosmic evolution. If they achieved similar technological sophistication to us around the same cosmic epoch, they would be observing the Milky Way as it appeared 2.5 million years ago, just as we observe Andromeda as it was 2.5 million years ago. Any communication between our civilizations would involve time lags of millions of years, making conversation impossible, but potentially allowing the exchange of information across the ages. Using Andromeda as a laboratory for understanding galaxies extends to theoretical, astrophysics, and computational modeling. Large-scale cosmological simulations, which model the formation and evolution of structure throughout the universe from shortly after the Big Bang to the present day, produce thousands or millions of simulated galaxies. Andromeda serves as one of the key observational benchmarks for testing whether these simulations reproduce reality. Researchers compare simulated galaxies to Andromeda's observed properties, including total mass, stellar mass, dark matter, halo mass, disk scale length, bulge size, rotation curve shape, satellite galaxy population, metallicity gradients, star formation history, and many other measurable quantities. When simulations match observations well, we gain confidence that the underlying physics is being captured correctly. When discrepancies arise, they point to areas where our understanding is incomplete, or where the simulations may be missing important physics. For instance, early simulations produced galaxies with overly massive bulges and insufficient disk structure compared to observations. This angular momentum problem suggested that simulations weren't properly handling how material conserves angular momentum as it collapses to form galaxies. Improvements in simulation techniques and the inclusion of additional physical processes like stellar feedback have helped address this problem, though challenges remain. Current state-of-the-art simulations can reproduce many of Andromeda's observed properties remarkably well, including its approximate mass, size, and spiral structure. However, getting all the details right simultaneously remains challenging. Some simulations match the stellar mass, but underpredict the amount of cold gas. Others get the rotation curve right, but produce too little star formation. The simulations struggle to reproduce the detailed structure of spiral arms, which likely requires higher resolution and more sophisticated modeling of how gas behaves under the complex conditions present in galactic disks. Each generation of simulations becomes more sophisticated, incorporating more detailed physics and running at higher resolution, gradually converging toward agreement with observations of real galaxies like Andromeda. The future of Andromeda research promises transformative discoveries as new observational capabilities become available. The James Webb Space Telescope, humanity's most powerful space observatory, launched in late 2021, will observe Andromeda with unprecedented sensitivity in infrared wavelengths. Webb's instruments can detect individual stars too faint or too obscured by dust for previous telescopes to see. This will allow astronomers to study stellar populations in Andromeda's dust-obscured regions, map the distribution of the oldest and coolest stars, and potentially detect brown dwarfs and very low-mass stars that have eluded previous surveys. Webb's spectroscopic capabilities will allow detailed studies of individual stars' chemical compositions, providing insights into Andromeda's chemical evolution history. Ground-based, extremely large telescopes now under construction will revolutionize optical and near-infrared studies of Andromeda. The Extremely Large Telescope, ELT, in Chile, with its 39-meter primary mirror composed of 798 hexagonal segments, will be the world's largest optical telescope when it begins operations in the late 2020s. The ELT will resolve stars in Andromeda with unprecedented clarity and obtain spectra of individual stars to determine their chemical compositions, ages, and radial velocities. This will enable detailed chemical cartography of Andromeda, mapping how the abundances of various elements vary across the galaxy and using this information to reconstruct its formation and merger history. The Giant Magellan Telescope, GMT, with 7 8.4-meter mirrors arranged to create an effective aperture of 24.5 meters, will provide similar capabilities from its site in Chile. The 30-meter telescope, TMT, planned for Hawaii with a 30-meter segmented primary mirror, will complete a trio of extremely large telescopes that will dominate optical and infrared astronomy in the coming decades. These facilities will enable studies of Andromeda that are currently impossible, including detailed spectroscopy of individual stars across much of the galaxy, direct imaging of star clusters, and potentially even detection of the brightest supergiants and peculiar stars that would stand out from the general stellar population. Future space missions dedicated to astrometry will measure the positions and motions of stars with extraordinary precision. While the European Space Agency's Gaia mission has revolutionized astrometry for stars in our own galaxy, measuring positions and proper motions for over 1 billion stars, Andromeda's stars remain too distant for Gaia to measure their proper motions. However, future missions with larger apertures and more sensitive detectors might achieve this goal, at least for Andromeda's brightest stars. Measuring proper motions would allow three-dimensional reconstruction of stellar orbits throughout Andromeda, providing unprecedented insights into the galaxy's dynamics and dark matter distribution. Advanced gravitational wave detectors will open entirely new windows on galactic phenomena. While current detectors like LIGO and Virgo primarily detect mergers of stellar mass black holes and neutron stars, future space-based detectors like LISA, Laser Interferometer Space Antenna, will detect gravitational waves at much lower frequencies. LISA will be sensitive to supermassive black hole mergers like the eventual merger of Andromeda's and the Milky Way's central black holes. While we won't be around to observe our local merger, LISA will detect similar events throughout the universe, allowing statistical studies of how often such mergers occur, how much energy they release, and what they reveal about galaxy evolution. These observations will test general relativity in extreme gravitational environments and potentially reveal unexpected physics. Next-generation radio telescopes, particularly the Square Kilometre Array, SKA, under construction in Australia and South Africa, will map neutral hydrogen in Andromeda with unprecedented resolution and sensitivity. the SKA will detect hydrogen gas in structures far smaller than current telescopes can resolve, revealing the detailed distribution and kinematics of gas throughout the galaxy. This will enable studies of how gas flows through galaxies, how it responds to spiral density waves, how star formation relates to local gas properties, and how galactic scale processes like gas inflow from the intergalactic medium and outflow driven by stellar feedback operate. The SKA will also detect many more radio sources in Andromeda, including pulsars, supernova remnants, and potentially new classes of objects. Future X-ray observatories with improved sensitivity and resolution will detect fainter X-ray sources in Andromeda and study known sources in greater detail. This will expand the census of X-ray binaries, supernova remnants, and other energetic phenomena. Advanced spectroscopic capabilities will allow detailed studies of the hot gas in Andromeda's halo, measuring its temperature, density, metallicity, and kinematics across the halo. This information will constrain models of galactic feedback and gas cycling between galaxies and the intergalactic medium, key processes that regulate galaxy evolution. As observational capabilities improve, theoretical models and simulations will continue advancing as well. Increasingly powerful supercomputers enable simulations with higher resolution and more sophisticated physics. Modern simulations can resolve individual star-forming clouds within galaxies and model detailed feedback processes, including stellar winds, radiation pressure, and supernova explosions. Future simulations will likely achieve even higher resolution, potentially reaching scales where individual stars, or at least star clusters, are resolved. These simulations will predict detailed properties of galaxies like Andromeda that can be compared directly with observations, creating ever more stringent tests of our theoretical understanding. Machine learning and artificial intelligence are beginning to play important roles in analyzing the enormous datasets modern surveys generate. When surveying Andromeda produces measurements of hundreds of millions of individual stars, traditional analysis methods become unwieldy. Machine learning algorithms can identify patterns, classify objects, and extract information from large datasets more efficiently than traditional methods. For instance, neural networks can be trained to identify different types of stars based on their colors and brightnesses, classify galaxies based on their morphologies, or detect subtle signals buried in noise. As AI techniques continue advancing, they'll likely become increasingly central to astronomical research, helping astronomers make sense of the unprecedented volumes of data modern instruments produce. The philosophical implications of studying Andromeda deserve reflection. This galaxy, visible as a faint smudge to the naked eye, represents an entire stellar system comparable to our own, containing 1 trillion suns and presumably trillions of planets. Some of those worlds might harbor life, perhaps even intelligent life, capable of contemplating their own existence and place in the cosmos. Yet these potential beings are separated from us by an unbridgeable gulf. Even if we could somehow send a message at light speed, it would take 2.5 million years to arrive, and another 2.5 million years for any reply. Any civilization we might contact would be separated from us by 5 million years of history, evolutionary changes, technological development, and cultural evolution. This realization highlights both the vastness of the cosmos and the preciousness of our local existence. We are cosmically isolated, alone not just on our planet, but effectively alone as a galaxy. The Milky Way is our cosmic home in a way that transcends mere location. Any other beings within our galaxy are at least potentially contactable, with communication times ranging from years to tens of thousands of years depending on their location. But beings in Andromeda or more distant galaxies are, for all practical purposes, permanently out of reach. We might observe them indirectly through their effects on their galaxies, but communication or interaction will likely forever remain impossible. Yet this isolation, rather than diminishing the value of studying Andromeda, enhances it. This galaxy represents the closest we can come to seeing our own Milky Way from outside, to understanding galactic structure and evolution through an external perspective that our position within the Milky Way cannot provide. Every observation of Andromeda teaches us something about galaxies in general, and thus about our own cosmic home. Every star resolved in Andromeda, every globular cluster catalogued, every stellar stream traced, adds to our understanding of how galaxies form, evolve, and eventually merge into new configurations. The eventual collision between Andromeda and the Milky Way, while billions of years distant, serves as a reminder that the cosmos is dynamic and evolving. Nothing is permanent on cosmic timescales. Stars are born and die, galaxies collide and merge. Even the universe itself evolves from its hot, dense beginning toward an increasingly cold and diffuse future. Our observations capture a single moment in this vast temporal expanse. Andromeda, as we see it today, frozen in an image showing its structure 2.5 million years ago, represents just one frame in a cosmic epic billions of years long. The galaxy has changed since that light was emitted, and it will change dramatically in the billions of years to come. Understanding this cosmic context changes how we see our place in existence. We are temporary patterns of organized matter and energy, arising from and eventually returning to the cosmos that spawned us. Our lives are infinitesimally brief compared to galactic timescales, yet we possess something apparently rare in the universe: the ability to understand these vast scales and processes, to reconstruct cosmic history from observations, to predict the distant future, to know that we exist as part of something incomprehensibly larger than ourselves. This capacity for understanding might be unique to intelligent life, wherever it arises in the universe, making it something of genuine cosmic significance despite the brevity and apparent insignificance of individual existence. Andromeda will continue fascinating humanity for as long as we exist to observe it. Each generation of astronomers discovers new details, answers old questions, and raises new ones. The galaxy serves as both a scientific laboratory and a source of wonder, a reminder of the vast cosmos beyond our small planet. As technology advances, we'll see Andromeda with ever greater clarity, resolving fainter stars, detecting subtler structures, measuring more precise properties. Yet no matter how much we learn, Andromeda will likely retain its capacity to inspire awe, that same sense of wonder ancient observers felt when they first noticed that faint, mysterious patch of light among the stars. In the end, studying Andromeda represents one of humanity's noblest endeavors, the attempt to understand the universe and our place within it. From ancient astronomers who simply noted its existence to modern researchers mapping its structure star by star, humans have sought to understand this neighboring galaxy. We've measured its distance, determined its composition, predicted its collision with our galaxy, and used it as a laboratory for understanding galactic physics. Through these efforts, we've expanded human knowledge from our immediate surroundings to encompass structures millions of light years across and timescales of billions of years. This expansion of understanding, this reaching beyond our immediate experience to grasp cosmic truths, represents something remarkable and perhaps unique in the universe's history. The ability of matter to organize itself into forms capable of understanding the cosmos from which it arose deserves recognition as one of the universe's most extraordinary properties. And Andromeda, our nearest major galactic neighbor, provides an invaluable window through which we can explore this remarkable universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.